Oh.
Hey.
Okay, so let's begin day two. So Professor Ross will continue with his meeting course on science.
Okay, thank you. Yeah, welcome back, everyone. Thank you for coming. So, right, this is where we ended last time, more or less. So let me just remind us all where we are. So again, this is kind of for the second time, a new talk for the second time. So last time we derived this theorem here at the bottom of the slide. So let's just go through it carefully. Today, we're going to be largely concerned with just applying this theorem in a bunch of examples. Okay, so let's remember we have some random variable W. It's just a sum of Bernoulli random variables with some dependence that is inherent in the problem. The mean we write as lambda, which is just the sum of all these p alphas, the probability that Bernoulli's equal to 1. And then we have this size bias construction in this setting. And the size bias construction is that for each index alpha, we have we're given, or we think we have to construct these x beta alphas, where the x beta alphas have the same distribution as the x betas given x alpha is equal to 1. Okay, so these just have the conditional distribution of the whole sequence given x alpha is equal to 1, and this encodes the dependence here. And then to construct this size bias distribution of W, we choose an index random. The probability that we choose index alpha is proportional to its mean, which is p alpha, and then we normalize by lambda to make those probabilities 1. And then we just set WS to be 1 plus the sum of all the betas not equal to the index we chose of these x beta i's. Okay, and this 1 you can think of as almost like this is like x alpha, right? Because the distribution of these is is conditional on x alpha equals 1. So it's sort of like we force this thing to be x alpha to be equal to 1, and so there should be a 1 here. Okay, so that's what it is. And then if we can construct such variables on the same space, these x beta alphas on the same space as the original x betas or the original x's, then we have this bound on the total variation distance between our sum of Bernoulli's and are Poisson with the same mean, which is given by the right-hand side here. There's this prefactor that's quite important. And then we have this average over alpha, P alpha. And then we look at the, we have this X alpha here. And then this term is really looking at how much the X betas have changed after we force X alpha to be equal to 1. Okay, so that's what we talked about that last time. Okay, so this is what we have, and now we just want to apply this in examples. Why is this useful? How do we apply this? All right, so this is actually where we ended yesterday. So the first thing is that, well, what happens if all the X alphas are independent? What bound do we get? And we saw that if we apply this when the X alpha is independent, then we can set the X beta alphas to be X beta because the conditioning has no effect. And so this term is 0, and we recover our thing we derived before, which was that the bound is just the minimum lambda inverse in 1, and then the P alpha, the sum of the P alpha squared. And that's sort of like a quite optimal bound in that case. Okay, I want to talk about something a little bit that we'll come back to when we do normal approximation called local dependence, which I'm not going to say what that is exactly now, but I will later. But this bound can be quite useful in the presence of local dependence. So local dependence means that somehow, X beta only depends on the other Bernoullis that are sort of nearby in a sense, okay? And then it's not dependent on far away Bernoullis. All right, so let's just do an example. Yeah.
Like we're assuming there's this kind of like conditional and varied for the X beta, right? Like if like for any alpha, if you have X alpha, the law of X beta is the same as the conditional law of X beta given X alpha equals 1. So like does that what basically what I'm trying to understand is like what kind of like restriction does that put on the dependency that the X betas have? Because like the X betas can't just be like dependent in any arbitrary sense.
They can be, yeah. I mean that's there's no restriction. I mean this is some distribution on the left-hand side, and that distribution is exactly the X betas given X alpha is equal to 1. The restriction is we need to construct these X beta alphas on the same space as the X betas. So because we're subtracting. So that's the difficulty in applying this is in a given application, how do I construct the X beta alphas on the same space so that they're close to the X betas? I mean, obviously you can't always do that. Or else everything would look Poisson. But in situations where something's close to being Poisson, you should be able to do that. Okay, that's the restriction here. It's really the construction, not the distribution. Okay, so here's the example. So this is a very concrete example. We're going to look at a sequence of Bernoulli random variables, and we're going to look at the number of head runs of length at least k. Okay, so we have this underlying sequence yi, I equals 1 to n. They're IID Bernoulli. So we have, I'm going to just do this like this: y1, y2, y3, y4, so on, and then we have yn. And what we want to do is we get a sequence. I mean, I don't know, maybe 0, 1, 1. Know how random this is, something like this. And what I want to do is I want to say how many head runs of length at least 3 does this sequence have? Okay, so we go here. These are, okay, ones are heads as usual. So here we have 2 1s in a row, but not 3. So that's not a head run. But here we have 3 head runs in a row. So that is a head run. So let me just continue this, something like this. Okay, so we get one sequence here of length of head run of length at least 3. We have another one here, right? And I want to encode this. How would I encode this? To count the head runs, I want to write it as does a head runs of at least length k start here in position 1? Does one of at least length k start here? And so on in position 2. And if I want to do that, what I need to do is, let's go here. Well, what I need is a 0 and then at least 3 1s, right? So every time I see the pattern, like here, I have x4, or sorry, I have a 0, 1, 1, 1. Then I will count this head run. If I have 0, 1, 1, 1, even more, that's okay too. And so what we want to do is we look at 1 minus y4 times y5, y6, y7. And if I look, anytime I see a pattern like this, I've started a head run length 3, right? And I don't care what happens after that. If it's a 0 or 1, I still have one of length 3. And the point of doing this 1 minus y4 is because in this case, if I just had y5, y6, y7, or whatever these are, I would count twice, right? Because once I have one of length 4, if I just look at the product of these 3 Bernoullis, then I'll overcount when I have one of longer than length 3. Okay, so this is called, we're sort of declumping these head runs.
Wait, what's the point? Would it also make sense to have like 1 minus y4, y5, y6, y7, 1 minus y8?
No, because it's at least 3. At least 3, yeah. So I don't care if it keeps going. Okay, and then to make the problem simpler, like, well, the first one should be a little different. It should be y1, y2, y3, because here, and then there's something happening at the end where I need to adjust these things. But to make the problem symmetric and just the calculation slightly easier, we're going to use this torus convention where ym plus j is yj. So just imagine I drew these in a line, but imagine I drew them in a circle. Okay, and we just want to see, we want to count how many clumps of ones there are that have length bigger than 3. Okay. So, you might think this is a contrived problem. This statistic is actually one that's the basis of like sequence comparison. So basically you have 2 sequences and you line them up in some way and you want to say, are these sequences close or not? Well, whenever they match you put a 1, and when they don't match, you put a 0. Okay, and so then you can come up with statistics that'll sort of measure the closeness of the sequence. You just count the number of ones. Well, maybe you get a sequence that's sort of like 1, 0, 1, 0, 1, 0, 1, 0, but somehow the sequence are generated in a certain way that means they're not close, like DNA or something, where there's some, we know that things come in clumps in DNA, and so if you get 1, 0, 1, 0, 1, 0, that's not a place that's actually counting things. And so when they were doing in computational biology, they did DNA comparison. They were interested in this statistics of these kinds of head type statistics, like how long a head run do you have to see before you can say, oh, this sequence is close, or maybe you want to do alignment, and so you want to line them up, and you want to use this as a measure of we did a good job of aligning them. They have a lot of long head runs, and in this case it's IID Bernoulli P. That's not very realistic for DNA or whatever, but this is just some kind of null model. Okay, so this is a model. This type of is a model that people care about. Okay, so then you can see what we're going to look at are these xi's, which are these sort of the indicator that a head run of a length at least k here happens at sorry, this was k equals 3. I should have said that. Happens at position I, and we sum them up. All right, and they're dependent, but they're locally dependent, right? Like, because this is x4. It's a function of y4 through y7. But if I look at x8, what is that? That's a function of y8 through y whatever, 9, 10, 11, y11, right? x8 is 1 minus y8 times y9, y10, y11. And so these are independent because they're functions of independent things. And so there's dependence, but it's local dependence, right? So oh, you're right. You're so right. 3. Thank you. Okay, so then this actually, what I had is what I wanted, but this is y4. This should be x5, and that should be x9. Okay. Yeah. Right. These are, this is why I'm not a statistician, Okay, so, yeah, so that's what we're interested in. So there's dependence, but there's local dependence. Okay, so now we want to apply this theorem. Okay, and we already saw something kind of like this. So how do we apply the theorem? We need to construct these x beta alphas, right? And what was the distribution of x beta alpha? So given what we're going to do is the whole y sequence. So this is like we did before we talked about last time with isolated vertices. We don't construct them directly. We don't construct the conditional xi's from the original xi's. We construct them from the original yi's. So given yi, I equals 1 to n, if I want to construct these random variables, xji, j not equal to I. So this should have the conditional distribution of the xj's given xi is equal to 1. What do I need to do? So, well, the event that xi is equal to 1, just the event that yi minus 1 equals 0, yi equals 1, yi plus k minus 1 equals 1. These events are the same, right? So if I'm gonna condition on this occurring, I must have this happen, right? But now, if you think about in terms of the original yi's, if I say all these have to be one, and then I want to look at the distribution of the rest, well, they're all independent, so I just don't change them, right? So given these, to construct xji, the set, yi1 equal to 0, yi plus k minus 1 equal to 1, and leave the rest of the y's the same. Okay, right? Does that make sense? I'm being very hand wavy, but that's the, this is. Okay, and then we set xji just equals the indicator that that we get a head run of at least length k at position I or j in the new sequence. Okay, in the new sequence, meaning where we've set these guys. Okay, so is that clear? So we have the yi's, and then we sample them. That gives us the x's, and then we pick our little I here, and we once we've done that, we set all these indices of the y's like this, and then we don't do anything else. All right. Okay.
Sir, can you please focus the camera on the second board? Thank you very much.
Sorry, I didn't quite. Did anybody get that? Oh, you got it? Okay.
I have to focus the camera.
Good, we got it. Thank you. Yes. All right. Okay. So now we want to bound this thing. So we need to look at this. Okay, x alpha, that's fine. We're not going to worry about that. You never have to worry about this one because it just gives you a factor of p alpha squared. It's really these differences you need to understand. But let's say, so what's xji minus xj? All right, there's two cases that can happen, and this is for j not equal to I, right? So this is all j is not equal to I. We don't worry about that. So we have to look at these. So what can happen here? Well, if j is far enough away from I, we haven't changed any of these underlying Bernoullis, these y Bernoullis, and so it'll be the same, right? So this will be 0 as long as I minus j is greater than, what do you guys think? K, right? And K. Okay, because then there's just no overlap. We haven't changed anything. They're the same. Okay, now if there is overlap, then one thing you have to think about, and one thing you might notice if you think about this, is that if in this one, I've forced a head run to start, a head run of at least length k to start at position I. And because of this declumping thing, these 1 minus, if a head run starts at, let's say position 3, another one cannot start at position 4, right? So there's some negative dependence here that's quite strong. And it's quite strong in the sense that if a head run starts at position I, one cannot start at position j when I'm within k, right? So in the new sequence, this is 0. So then this is negative xj if I minus j is less than or equal to k. Okay. So this is the, this is what we get. And now we can, this bound's quite simple, right? So then the bound says that the total variation distance of w and z is less than or equal to this minimum of 1 in lambda inverse, and then times the expected value of, sum I equals 1 to n of pi times the expected value of xi plus the sum j not equal to I minus j less than k of xj. That's what we get. Yeah.
I agree. So the xi the indicator of what's the precise material on the copy.
Here?
Right at the top, right.
Oh, that's the indicator that a head run least length k at position j. Yeah. It doesn't. Yeah, in the new sequence. Okay. I should say starts. starts at position J in the new sequence. I'm well aware my handwriting is very bad. I'm actually working hard on it. This is good. This is good for me. But please stop me if you can. Okay, so this is what the bound is, and then okay, this is positive. I can take the absolute value away, and so I get well, we have to figure out what pi is, but you will get a pi squared and then a pi pj for these things. Because of symmetry, because we have this, all the pi's are the same, right? The probability of a head run starting in position I is doesn't matter where I is because we put it this torus convention. And so then what's pi? Okay, so to bound further, just note that pi is equal to, what's the probability a head run starts at position I? Well, it's just the probability this xi is equal to 1, and that's just well, 1 minus p times p to the k, right? So this is just the probability that the yi minus 1 was equal to 0, and then this is the probability of the rest, the k after that are equal to 1. Okay, they're all the same. And so then this is less than or equal to this minimum of 1 in lambda inverse. And then we get an n times this p, 1 minus p times pk squared times the number of terms we have here, which is sort of 2k plus 1. Okay. 2k plus 1, 2k minus 1. Let's say 2k. This should be less than or equal. 2k plus 1. And then lambda is this n. Yeah, that's right. And this is equal to lambda's then is equal to n times this thing. Okay. So I mean, yeah, this is what we get. And if lambda is bounded away from 0, then we sort of have a lambda sitting here, right? So let's just take this lambda inverse and say lambda is bounded away from 0. If lambda is close to 0, Poisson approximation is always good because everybody's 0, right? We have non-negative integer valued random variables, and the mean is very close to 0. It's 0. You don't need to worry about this. So somehow let's just choose in this minimum this lambda inverse, and then there's a factor of lambda right here. So then this is less than or equal to 1 minus p times p to the k times 2k plus 1. That's right. No, something's not quite right here. Okay. And then let's write this as lambda over n. That's maybe the clear way to see it. This is always the rub here, as we'll see today. Is like you do these calculations and then you say, okay, well, when is this going to 0? Okay, so if lambda is stabilizing, this is going like k over n. Okay, and so you can see, you can actually even, this look Poisson. I mean, it's not surprising if k is fixed that this thing is going to look Poisson, but this bound says is you can actually let k go to infinity with n. It just can't go as fast as n, and this will still, as long as lambda is stabilizing, it will still converge to 0. Okay, so that's a really important feature of these types of bounds. So I'll even remark it down. Bound shows that k can go to infinity with n, and the total variation distance still can go to 0. Okay, they have to be careful about these things because lambda may be growing as well, but anyway, I'll leave that kind of analysis to you guys to look at.
Sir, can you please read out the remark again?
The bound shows that as k goes to infinity with n, so we can let k go to infinity with n, and the total variation distance may still go to 0. So here, because this resulting bound here has this k over n here. Okay. Yeah.
Paul saying that for the science method we use to show that.
Oh, for lower bounds? That's a good question. So lower bounds are harder in general. There's a couple ways to do them. You can do them in an ad hoc way. You can just find some event that separates these things. You can use Stein's method. It's not as systematic and it's not as easy where you 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 essentially do the same thing. You pick a test function for your total variation distance, and then you lower bound the same thing we're bounding here, this lambda f of w plus 1 minus f of w, but you have to be more careful about it, and you have to really use all the properties of that test, of that Stein solution, right? Because it's equality. So I can go back here. See, this is an equality, right? So if I can fix an h and then lower bound this thing for that f sub h, that'll still give me a lower bound. But this is not so easy, I should say. This is much harder to do. Yeah. So and for this problem, I'm not sure. I mean, this is a very well studied problem actually. So I think it is going to be known, you know, the regimes where k and n, how k can go to infinity with n and still get some kind of Poisson convergence, and there will be some lower bounds like in the literature, but I don't have these references on the top of my head. Okay, there was another question, yeah. Well, I mean, I guess what I should say is this is completely, like this bound is completely explicit in P and K, N actually, but I'm saying I just rewrote it with the lambda here, which has the N and the P, but this only depends on N, P, and K. So the whole bound just depends on N, P, and K. That's the way, like that's another thing to say is that even without doing any asymptotic analysis, if I knew what P was, I knew what K is, this gives me a number, right? If this number is small, then the total variation distance is small. Okay, it's just somehow, you know, analytically you see this and you say, well, when is this going to be small? We want to get a rough idea of what lambda and k and n have to do. Okay. So yeah.
Sir, is this bound tight?
Someone else already asked that. I'm not sure if the bound is tight. No, but people have studied this problem a lot, and so I think it will be known more or less when the bound is tight. Yeah, or when a bound like this is tight.
Okay, thank you.
Okay. So, and then you can do further things like, what if I really wanted to say, you know, one regime that's always interesting is when does lambda actually stabilize? When does lambda, like this is lambda, it depends on n, p, and k. When does this converge to something? So, you know, you can fix p. If we fix p and send n, fix p and k, we send n to infinity, it's going to go to infinity, right? So that's one regime. But what we could do is we could let p go to 0, fix k, and then let p go to 0 at just the right rate so that it balances, right? And so you play around with these things and do this.
P like constant, right? If P doesn't depend on n, then it's in like the open 0, 1. Then lambda would go to 0, right? Because P to the n would dominate.
But this is a k. This is a k.
Okay, then.
Yeah. So there's three parameters. There's p and k. So if you fix p and k, then it's just order n.
Yeah.
Yeah. So
P depend on n and the k to 0 is the right.
Yeah, and we could do the same. We could fix p and let k go to infinity at the right rate to balance the n, right? Some log p thing. So so these are all things you can play around with. I encourage you to do that. But yeah, I don't want to do a really thorough analysis just to show you how to apply these things. Okay, good. Any questions? Yeah.
Would it be difficult to expect that instead of overlation, if you chose some other distance measure, you would get up the constants or something?
Yeah, let's see. So, I mean, here we're comparing two integer valued things. So total variation distance is a quite natural measure and it's very strong, right? But maybe you're interested in the Wasserstein distance, but even for that, you know, because we're on the integers, the Wasserstein distance is sort of, you know, it's kind of the same, yeah. Well, it'll be bigger potentially, but it's probably going to be pretty much the same because the test functions for the total variation distance are also Lipschitz, right? Lipschitz 1, yeah. So in general, people just use total variation distance. I mean, there could be a situation where total variation distance is too strong and you want to look at like tail probabilities or something and like, you know, Kolmogorov type distances compared to CDFs. But, you know, typically in integer comparisons, total variation distances. Because total variation distance is the same as weak convergence for two integer valued random variables. So somehow it's kind of a they're typically this is not too strong, and yeah. Other questions? Okay, great. So let's keep on with these examples. Okay, so there's a couple really nice things that happened. It actually happened in this example. We'll come back to it in a minute. When these couplings are increasing or decreasing, and when they're increasing or decreasing, the bound really simplifies because you can write it in a certain way. You can sort of, like what happened last time was these were all negative, right? So then this absolute value became positive, and we could just evaluate it directly. And so if you sort of go back to the construction, what that means is we could almost have removed the absolute value here, okay? And then the expected value of this w plus 1 minus ws is just some function of the first and second moments, and so things simplify. So okay, so let's do the first one. This is increasing couplings. So increasing couplings. So this is again just the same bound we had before. So if the construction that we do is such that the x beta alphas are always bigger than or equal to x beta, so these are Bernoulli's. So that means that if x beta is equal to 1, x beta alpha is equal to 1, we sort of can't erase these events occurring by doing this conditioning. Then this total variation distance has this simpler form where we look at this minimum 1 of lambda, and we get the ratio of the variance of the mean minus 1 plus this kind of term that looks a lot like the independent term, the sum of the p alpha squares, which is that's a good bound. That's what we see in the independent case, so that's okay. And this bound's quite natural because, I mean, just a kind of rule of thumb, if something's going to look Poisson, the variance and the ratio of the variance and the mean should be tending to 1. Okay, it should be very close to 1. If that doesn't happen, it's not a proof, but if that doesn't happen, it's probably not going to be Poisson. Okay, and with any sort of higher moment integrability, it is a proof. You can't if something converges to Poisson and you have uniform control over 2 plus delta moments, then the variance has to converge to the Poisson variance, and the mean has to converge to the Poisson mean. Okay, so this is a very natural bound. All right, so I guess I will prove this, but maybe let's just say like this gives us some things very quickly. So let's say we're considering W, which is we're counting various statistics in the Erdős-Rényi random graph. And what are some statistics that are increasing? So what about the vertices have degree no greater than k? So what we're doing is we're counting the number of vertices whose degree is k or k minus 1, k minus 2 down to 0, right? Now, when we do the coupling, I'm just going to describe this because I don't want to get in too much detail, but if we do the coupling, we're going to choose a vertex, and if it has degree less than or equal to k, then we leave it. We don't do anything because we have to condition it equal to 1. We have to condition the indicator that vertex has degree less than or equal to k equal to 1. Okay, if it's like that, then we don't do anything. And then if it has degree greater than k, then we have to erase some edges. Okay, the way we erase the edges, it's got to be random. It's maybe a little complicated, but we have to erase some edges to make the degree be less than or equal to k. If we erase edges connected to this vertex, the only thing that can happen is other vertices' degree can go down, and that makes them more likely to have degree less than or equal to k, right? Okay, so that's an example of an increasing coupling. And now for that coupling, we don't actually have to really even construct the coupling like in detail. We just have to say, oh, that's this increasing coupling. Now all we have to do is compute the means and the variance of that statistic, which we can do in the usual way. I mean, it's going to be n times the probability a given vertex has degree less than or equal to k, which is some binomial probability because the degrees of vertices in the Erdős-Rényi are binomial. And so we can write these things down. And so, we automatically get an upper bound on the total variation distance between the number of such vertices and the Poisson with the same mean. Similarly, vertices having degree no less than k, it's the same argument, except the other way is that we're counting now vertices who have degree k or k plus 1, k plus 2, etc. And we go through here, and then when we condition one of those vertices to have degree greater than or equal to k, all we're going to do is add edges if we do anything. And if we add edges, that increases the only thing it can do is increase degrees of other vertices, and that makes them more likely to have a high degree, right? So it's the same argument. And then if we wanted to do subgraph counts, which is again an important subgraph counts are an important statistic in various. We already talked about this actually in various network sciencey type things where they're just summary statistics for graphs. it's the same idea as we write our random variable W as a sum over the indicator at this position, we see that subgraph H, and then at this position, we see that subgraph H, and we sum over all those things. And now if we want to condition one of those, one of those positions to have the subgraph H, what do? We just add any edges that aren't in H. And if we add edges, it only makes other copies of H more likely. Right? And I should say we're not doing induced subgraphs here, so it's like, yeah, we don't care if there's extra edges. Yeah. Okay. So that's important for this thing. No, a position. So okay, I'm actually going to do an example of this in more detail. So let's do that. Okay, so let's just quickly prove this. I mean, there's really nothing to do. We just take the previous, we take this bound that we have right here, and then we use the fact that we know that all of these are non-negative, and we just use the triangle inequality. So just a quick proof of the bound, proof of the increasing coupling bound. So we just use the box, use the box at the top, and so we know that our total variation distance is less than or equal to the minimum of 1 in lambda inverse. And now because as I said, this is all non-negative, we'll use the triangle inequality. We'll just make it x alpha plus the sum of all those things. Okay. Okay. That. Okay. Not my most beautiful here, but all right. And so we're just, using the triangle inequality and using make everything positive. And so this is P alpha. What is X beta alpha? X beta alpha is the probability X beta is equal to 1 given X alpha is equal to 1. Yeah. Right, so let me just keep writing here. And then so we get a P alpha squared plus P alpha times the probability that X beta is equal to 1 given X alpha is equal to 1, sum here, minus P alpha P beta. Okay, and so we have here. Okay, but then you can see this is the probability X beta is equal to 1, probability X alpha is equal to 1. So this is almost the variance, except I need the cross terms, right? This is the covariance of X alpha, X beta. That's what this whole term is. That's just the covariance, and I'm summing up over all betas and alpha, covariance X alpha, F beta, then I get the variance, but I don't have the cross term or the diagonal. I have the cross terms. I don't have the diagonal, right? So I just add and subtract that. Okay, but the diagonal is just the variance of X alpha. So that's P alpha 1 minus P alpha. Plus the variance of W. Let me do it like this. So it'll be minus P alpha 1 minus P alpha plus the variance of W. So I'm just going to add and subtract the term here. And then something's a little off here. What's happening? P alpha squared here. That's right. Oh, no, this is okay. Yeah, this is looking good. Just have to remember what I'm trying to prove here. Okay, and then this is P alpha squared, and so we get a 2 here. And then now we have this minus P alpha. We're summing over alpha. That's minus lambda. And we have this minimum 1 lambda inverse. Let me just do it like here. Minus lambda plus the variance. Okay. And then that's what's on the slide. Well, okay. I've removed, oh no, I still have it, yeah. So now we just multiply by lambda and divide here and we get what's on the slide, right? Is that okay? It's not really, I mean, we could just prove it, you know, this is the bound. It just happens to simplify to this. It looks nicer, right? Okay, so let's just do some quick examples. So I've already mentioned these examples. We'll do copies of triangles, but let's do the isolated vertices. Remember last time we talked about isolated vertices? Let's just do isolated vertices. Okay, that's actually having degree no greater than k is 0. So it's one example of that. Okay, so W equals the sum. Vertex I is isolated. And remember, we even did this one specifically. Like for the isolating case, it's easy. I choose to construct these x beta alphas. I choose a vertex uniformly at random, and I isolate it. I just erase all the edges, and that can only isolate other edges or other vertices, right? So this is clearly increasing. Okay, so from last time, we have a construction with x j I greater than x j. Okay, so that's what we have from last time. So now we can just plug in this bound. All we need to do is compute the mean and the variance of W, right? So, okay, so lambda is equal to n times 1 minus p to the n minus 1. That's the, like, is that can't have touched anything. So for the variance, so the variance of W is, let's just do one of these in quite detail. Okay, so we just expand, we use this linearity of covariance. So the variance is the sum of the sum, the variances plus the of all the covariances of all the crosses, right? And by symmetry, these are all, everything's the same, right? The variances are all the same, the covariances are all the same. And so then the variance equals n times 1 minus p to the n minus 1 times 1 minus p to the n minus 1. That's just the variance of a Bernoulli. And then the covariances, there's n times n minus 1 of these. And then what's the probability? Both I and j are isolated. Here's vertex I, here's vertex j. There's n minus 2 other vertices here. And we just have any of these edges or that edge or these edges, they not be there, right? So there's one edge here, n minus 2 times 2. So this is times 1 minus p to the 2 times n minus 2 plus 1. And then we subtract 1 minus this thing squared, right? The probability of the Bernoulli squared. Okay. Okay. Good. And one thing to notice right away is we have lambdas sitting in here. So as usual, we're kind of gonna you know, divide by this. Oh, so we dividing by this lambda. Oh, I should just say. So then the variance of W divided by lambda is this goes away, this n, and then some of these 1 minus p goes to away, equals 1 minus p to the n minus 1. Okay, so that's good. That'll cancel our minus 1 plus n minus 1. So we have a common, this is 2n minus 3, right? This is 2n 2. So there was so got a 1 minus p to the 2n minus 3, but then we're going to cancel n minus 1 of that. So you get 1 minus p to the n minus 2 times p, because then this will be 1 minus p, because they're all flat 1. Okay. So that's what we end up with here. Good. So then the bound becomes, so let me just write down what the bound becomes then. Right, so the bound is, so again, I'm just gonna, this minimum 1 lambda inverse, I'm just gonna replace that with 1, so we don't need to worry about that. And we subtract 1 from this thing, and we get n minus 1, 1 minus p to n minus 2 times p minus this 1 minus p to the n minus 1. I'll replace that n minus 1 with an n, 1 minus p to the n minus 2 times p minus 1 minus p to the n minus 1. And then we have plus 2. Well, this p alpha squared, all the p's are the same. So it's actually np squared, which is p on, which is lambda p, right? So we just get this p here, plus 2 times 1 minus p to the n minus 1. Okay. This is lambda. This is lambda on n, right? That's the idea here. Okay, so then this is the bound. I mean, it's totally explicit in P and N. We don't need to do anything. But again, like I was saying, is we, let's do a little bit of asymptotic analysis. I don't want to do a full thing here, but let's just think about what the size of this bound is. When does it go to 0? So the first thing to say is if P equals, let's say P is equal to C on N, then what happens? Okay, I mean, the mean is essentially, the thing to keep in mind is that the mean is like n to the p to the negative np, right? That's as long as p is going to 0. Quickly enough, if p is not going to 0, as we'll see, there's going to be no Poisson approximation. If p doesn't go, if p is just even going like c on n, then what happens is then lambda is like n times e to the negative c, and the variance is like n times, getting n times e to the negative c times 1 minus e to the negative c. And so there's no hope of Poisson approximation because if I have the means going to infinity, but the ratio doesn't tend to 1, it's not going to look Poisson. It's just not going to happen. So this is not a good regime. As we'll see later, normal approximation is appropriate in this setting. We have the mean and the variance go to infinity at the same rate. That's a very good clue for normal approximation. Okay, and then okay, so that's a bad regime. What are some other regimes we can look at? P is, so here we have n e to the negative np. We sort of need to cancel this n if we want this thing not to be rushing off to infinity. And so let's try p is c log n over n. So when we look at e to the negative np, we get n to the negative c, right? And this tells me lambda is like n to the 1 minus c. Okay. Okay, so c greater than 1. We don't care about that because then lambda goes to 0. So we don't want that to happen. And if lambda goes to 0, we don't really care about this, So it looks Poisson, that's fine. If c is less than 1, or I'll just say it's less than or equal to 1, then lambda is bounded away from 0. Okay, we'll do both. So c is less than 1. Okay, then lambda is like n to the 1 minus c, and it's going to infinity. And you can check the bound is like, sorry, I did it. It's like log n on n or something like this. Log n on n to the negative c. Log n on n to the c. So it goes to 0. Okay, so you have to plug things in, but you can probably see it on the board. I'm a little too close. But what we can see here is that this is a case, as I was saying before, with this bound, lambda is going to infinity. There's no Poisson convergence happening, right? But the total variation distance is going to 0, and we have a rate for how it's going to 0. So you can still say it's close to a Poisson, right? Okay, in this case, you expect, in this case, we also expect the normal approximation to be good, because what we're saying is this thing is close to a Poisson distribution with a large mean. That'll be close to a normal. But typically, what happens is in that case, for the normal approximation, the rate would firstly be in a weaker metric than total variation distance because we're comparing a discrete thing to a continuous thing. And it would usually be the square root of this because it's like the standard deviation, not the mean. So if in this case, even though the normal approximation will still be valid, we're able to get a bound that goes to 0 in a stronger metric and that goes to 0 faster. Okay, so that's a real, part of this. All right. So now we can say, well, what about, maybe we actually want this thing to converge or whatever. So, and we want lambda to actually converge and stabilize, so we can think about that. So the first thing you might think is, well, C equals 1. C equals 1, then lambda is going to be constant order because we're going to have this n e to the negative np. We have log n on n. We'll get then lambda is asymptotic towards 1. And again, you can check the bound is going like, I think it's like log n on n. Okay, so it's the same rate as this. Okay, here now there's actual convergence, but it's lambda equals 1. So maybe we want to tune this a little bit and say, well, I want a generic lambda. And so you can do a thing, So we choose p to be log n on n. And then we have to subtract off this alpha. No, it's log alpha over n. And then lambda is asymptotic to alpha. Okay, so then this is where we get Poisson convergence with any parameter that we want, and the bound is log n on n again. So this is the real sort of Poisson regime here. But I only say this, like, this is the kind of thing you can do when you get these bounds. I really want to emphasize the bound is totally explicit in N and P. So you don't really need to do this, but if you want to, say something kind of at a high level, then you should do it. And then also that you can get Poisson convergence, but even if you don't have convergence, the bound can still go to 0. All right, and that's really the power of this whole setup with the Stein's method. Okay. The total variation bound. Yeah, all these are just the total variation bound. Yeah. Yeah. I mean, you have to do a little, but you don't have to do that much of a calculation. This is the bound here, right? So the bound is like n e to the negative np times p, and then e to the negative np, or sorry, it's even better than this because there's a cancellation here. I should actually, right, I should have said this will cancel, one of these will cancel with this. So it's actually, anyway, so it's just these two terms. Yeah, exactly. Yeah. That's right, Poisson lambda, yeah. So as I said, if lambda goes to 0, we don't really care about that case. If lambda goes to infinity, you can still be close to a Poisson distribution. Yeah. But somehow tuning lambda is a thing to think about when you're comparing it to the bound. Okay. Yeah. I should say that's the intuition kind of thing. So, so firstly, there's just like, if P is too big, what happens is you have no isolated vertices. So that's sort of, even if C over N, P is too big to see a Poisson convergence because there's too much correlation happening in them. If it gets even bigger than that, you will have no isolated vertices. So you have these really sharp cutoffs that you can see. But the idea is P is small, like this one will be isolated, and surely that affects the other ones, but it doesn't affect them too much because the chance that any vertex, if P is less than order 1 on n, then the chance that any of the edges attached to here was going to attach to this is very small. So it doesn't really affect anything else. Like I isolate this vertex, I throw it out, the rest of the graph just looks like an Erdős-Renyi, but now there's only n-1 vertices. So that's the intuition. And the same with the degrees. If I tell you the degree of one vertex, yes, that affects the rest of the graph, but in certain regimes, it won't affect it enough. And we can think of this almost as a sequence of independent Bernoullis, weakly dependent Bernoullis. Well, so I had a minimum lambda inverse, and then I put the minimum 1 lambda there. So this whole thing needs to be multiplied by 1 over changes to 1 lambda. Sorry about that. I think it looks nicer here because it's like, as I said, this part of the bound is like this thing with this minimum 1 lambda with the 2 on lambda p alpha squared. That's like the independent bound we get. So there's no hope if that's not small. And then all you're left with is the ratio of the variance and the mean compared to 1. And that's clearly like the right thing for Poisson. It's very natural. Yeah.
such examples, if you do normal approximation by Stein's method, and alternatively, first do a Poisson approximation, compare the Poisson to a normal, which one we can.
Well, so as I said, the second, well, you would typically get the same thing, but the second way is much easier because the Poisson to the normal is easy to do, right? To get the rate there. But what I'm saying is that this bound is just smaller order than it's smaller order than the actual normal approximation bound. Somehow the total variation distance to this discretized thing is actually smaller order than in this weaker metric to this continuous thing. Yeah. But yeah, so in those cases, there's no reason to go do Stein's method for normal and from scratch. You might as well just do the triangle inequality. Yeah. Yeah, I was gonna say I should stop, right? Yeah. Okay, 10 minutes.
There will be a photo end of this talk. Yeah, after the talk. After the second report.
Okay. Okay. Continuing next session, yeah.
Follow-up question that what you asked. So
Uh-huh.
one can have weak distinction, weak convergence, right?
Yeah.
Of the normal approximation because that's bounded by relations.
Well, yeah. No, I mean this.
It doesn't mean anything. Total relation distance between normal and suitably scaled.
Yeah. That'll be one. Yeah, because it's discrete. You can't compare it discrete.
One can have weak distance. Because that is upper bounded by suitably scaled functional that isolated vertices and normal, right?
Yeah, total variation.
So
Yeah. So that'll go right. That's gonna go.
this is Poisson.
Or Poisson is but also normalized. Yeah. Yes. Yeah. So that will go to zero.
Yeah, so because total
Yeah.
you can forget about this. Yes, right?
That's right. Yeah.
So and Poisson.
Well, no. Sorry, you don't have the same color. This time is when they're off. You don't have this one.
Washington weak.
A week. Oh yeah. So on the
So
side. Yeah.
that is a question.
Very-
We converse, we can.
Or like, this was this Kolmogorov distance. Then it's
Yes,
then that's fine.
that is what I'm saying.
No, yeah, but what I'm saying, then if you want to replace this with the normal 0 variance 1, the distance from here to here is a bigger order than it would be the square root of that. Because this is to be sort of, you expect this to be, when I replace with this, I should get a term that's order 1 on the square root of that.
Yeah.
Whereas-
Use the traditional boundary. The Poisson and normal. Right.
You can just use a Ariesian now.
Yes, sir. Very easy. Yeah, that order would be the.
Yeah. It's smaller order than that, because in this case, lambda n is like this n to the 1 minus.
For instance, there is this fact that if you take a random permutation of n elements, and you look at the number of fixed points over the number of transpositions that are contained in the document, then as n goes to infinity, some scaled versions of these random variables, they converge to independent points on random variables with certain intensity. So is there a version of the Stein's thing?
Yeah. So there's a multivariate version. I mean, in broad strokes, I'm saying, you have a characterizing operator right now, you have found a solution for that. Founding the solution will be different because multivariate case, and then multivariate case, you can't write down the solution. But anyway, you can do it, and then the bounds actually are very similar. They're usually, they're sort of just the same. Take the marginals, and then there's a little bit for the cross term to make sure they're not too correlated. So yeah, that includes. But so I think like if you can digest this and understand this, you can create that better.
No, because the thing is that there are two books of that I have seen. The first is purely combinable. This is nothing apart from the fact that you can get a generating function which and then you can let that. So, yeah, that does not give you. But it's beautiful in the sense that you can use completely different tools.
Totally, yeah. Yeah.
That's more probably.
Yeah, probably. And then couplings and everything.
I wonder, especially for.
I can still do that.
There you have a little bit more dependence on samples from and you get that the degree distribution. Oh, sure. Oh.
solo கொஞ்சம் கரெக்டா வருது.
What I do? You don't do it.
சிக்னல் கிடைக்கலாம் எப்படி இருக்கும்?
Yeah, I sort of mentioned it very well, like I said, so.
To go off.
Oh, that, so, no, it's not this, it's to go, just to write this, cause I lose the absolute values. Yeah, it's the getting rid of the absolute values, that's the key thing, yeah. Okay. Yeah, that'd be great. Yeah. I'll leave this stuff up because it was just there.
Select this part.
Start. Okay. I've been told it's been 10 minutes and we're starting.
Yeah.
Are we ready?
Yes.
Okay. Okay, so as I promised Shiva, we have to do a subgraph counts. Oh, wrong slide. Still on this slide. Okay, so let's do copies of a fixed graph H. Okay. So so let's just say H is a triangle. This is kind of the easy to enumerate. Okay, then what we do is we write W is the sum over alpha in what I'll write as gamma of X alpha, where this gamma is just the so gamma is the set of triples of vertices. I should just say a subset of n. Okay, so for any three vertices, we look there, and if all three edges are present, then we count the triangle that's there, and we just do this over all the graphs. I don't know. I mean, I could write this. We could do this a few ways. We could write this as the sum of X, I, J, K. Okay, again, there's a lot of symmetry in the problem, so we're sort of we kind of want to just avoid writing these things in too much detail. Okay, so this is the setup now, and what do we want to do? We want to apply this theorem. So what's this? How do we generate these? You know, so in the usual way, we generate G sub n, which is Erdős-Rényi parameters n and p. Now we want to we want to generate a graph that a Gn alpha that has the distribution of Gn conditional on having a triangle at alpha. And I mean, just to skip some steps here, well, what are we going to do? Well, we just have to add the edges that are at alpha. That again, that event that X alpha equals 1 is just the event that all three of those edges are present, so we have to add those in. But then once you notice I add them in, all the other edges are independent, and so that's all we have to do. So we generate this by adding the three edges, if they're not already there. At position alpha. Okay, so this is what I was saying before, and for general H, that's what you would do. You'd have some enumeration of all the places H could be, and then to generate this Gn alpha, you would just force H to be there by adding edges, okay? Triangles are a little, simple exceptions. Okay, and then as I said before, now we've added edges, and so all I can do is add triangles, right? So we let X beta alpha equal the indicator of a triangle at position beta in Gn alpha. Okay, and okay, then X beta alpha is bigger than or equal to X beta, since we just added edges. Okay, and then the theorem applies. And so, you know, I'm not going to do a full analysis, but let's just compute the mean and the variance. That's all we really need to apply the theorem. But this GTV bound is increasing GTV bound. Okay, so we just need to compute the mean and the variance, but again, by symmetry, it's just the number of triangles, potential triangles. There's n choose 3 places. And then what's the probability that at a given place we have a triangle, we just need all three edges present, and all of these things are independent Bernoulli, so we get a p cubed, right? And similarly, the variance of W, so this is p alpha, p sub alpha is p cubed, and the variance of W is, you know, similarly, we have the diagonal term, which is n choose 3, p cubed 1 minus p cubed, and then we have all the cross terms. How many cross terms are there? There's n choose 3 times, okay, so now the cross terms we have to be, let me not do all the cross terms. So again, by symmetry, there'll be n choose 3 And then for the sum over alpha, and sum over beta not equal to alpha, the covariance of x alpha, x beta, let's write it like that. Okay, for these, so there's n choose 3 terms in this sum. And then this will all be the same by symmetry, so we have n choose 3. But now we want to think, we're going to sum over all the betas not equal to alpha of this covariance of x beta, x alpha. Now, if the triangle position alpha and the triangle position beta don't share an edge, the covariance is 0, right? Because there's no, okay. So this, okay, so then the covariance of x alpha, x beta equals 0 if no edge shared by alpha and beta. Okay, and then what else can happen here? All right, so let me just draw a picture. So this is what the picture looks like. You know, here's my alpha triangle. Beta's out here. They don't share an edge. Okay, maybe I'll even make beta. They can share a vertex. That's cool. That's fine. So there's my alpha triangle. There's my beta triangle. Still, covariance is 0 because they have no edges in common, right? So now if I want, which ones do have edges in common for a given alpha? Here's my triangle alpha. I have n minus 3 other vertices. Let me put that there. And the only way, you know, for triangles, they either share 0 edges, 1 edges, or 3 edges. You can't share 2 edges, exactly 2 edges and be a triangle, right? So there's 3 potential edges here, and there, for each of those edges, there's n minus 3 other triangles, right? Potential triangles. Okay, so the number of non-zero terms in this sum is 3 times n minus 3. Right, so for each edge here, I have, you know, this is one beta that is correlated, this is another one, this is another one, and so on, and then I can do the same for all these other edges. Right. Okay, and for those, what's the covariance? Well, it's the probability both edges are both triangles are present. So this is what we have, the alpha, looks like this. This is our alpha, this is a beta, they share one edge, and so that's 1, 2, 3, 4, 5. I need 5 of those edges to be present, and then they'll both be present. So that's the expected value of x alpha, x beta.
Only when 2 edges are shared.
When one edge is shared, 2 vertices are shared. Yeah. Okay, so then this is p to the 5th minus p to the 6th, which just equals p to the 5th. Okay. So I'll just write it down. So the variance of W is just n choose 3 times p cubed times 1 minus p cubed plus n choose 3 times n minus 3 times p to the 5th times 1 minus p. And again, there's a lambda factor sitting in here. So this equals lambda times 1 minus p cubed plus 3n minus 3 times p squared times 1 minus p. As lambda is n choose 3 times p cubed. Okay, so then when I divide by lambda, I have a 1 minus p cubed, blah, 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 and this 1 will cancel with the minus 1 there. And so then the bound, it's actually just like what's going to happen here. I have a plus, and then I have this minus, but that minus is exactly what's this positive term at the end, and there's 2 of those. So the bound is less than or equal to 3 times n minus 3, p squared times 1 minus p plus p cubed. That's what you get. Okay. Okay, and then this will go to 0 as long as p is little o of 1 on the square root of n, right? Okay, because this is going to 0 as long as p is going to 0, and then we have an np squared here. Okay, so and that's it. And we could do a similar thing. Oh, when is the mean growing? When's it constant order? This kind of thing. And you can do a really thorough analysis. Okay. So I should say, I didn't say this last, but all of these examples, I mean, they're in my survey, but they're also in much greater detail, especially this asymptotic analysis in the book by Barber, Holst, and Janssen. So, that's really where I'm giving kind of light touch to all this stuff because I just want to get the high level ideas. But if you want the details, they are really written in quite a high level in that book. Okay. Okay, good. So, all right. So, okay, one more. We have one more, and then we're doing normal approximation. Okay. Any questions so far? Okay. So the next one is decreasing couplings. Decreasing couplings are it's like increasing couplings, but they're decreasing. So now we have the same thing. We have the same bound, but now if we can construct the thing so that x beta alpha is less than or equal to x beta, then we get this very simple bound where all that appears is the ratio of the variance and the mean and its comparison to 1. Okay, that's all you get here. So, I mean, the fact that this is decreasing coupling is, there's no absolute value here, right? So somehow this is non-negative, but that's coming from this negative dependence that we're getting. Okay, so the proof is, maybe I'll just quickly prove it. It's the same as what we just did. It's actually just a little easier. So in the increasing case, and then I'll just do one of these examples. So the proof of the UTV bound, it's just the same as before. We just plug in this thing exactly, but now this is decreasing, so this term is negative, and that becomes a plus, right? So x alpha minus the sum beta not equal to alpha of x beta alpha minus x beta. This thing's now less than or equal to 0, right? So let me put the absolute value here. And so this thing actually, in absolute value, because this is less than or equal to 0, this is x alpha plus the negative of this term. Everything's positive. There's no absolute value anymore. This equals x alpha plus the sum beta not equal to alpha of x beta minus x beta alpha. Everything here is positive. This is greater than or equal to 0. That's greater than or equal to 0. So I'm taking the absolute value and it goes away. So now when I take the expected value of this thing in absolute value, I just take the expected value of this. Equals. Okay, and then it's kind of the same. It's just, but now we get a nice, now we get a kind of nice cancellation. So then the sum over alpha of p alpha times the expected value of this thing in absolute value up here equals the sum over alpha p alpha times the expected value of x alpha plus plus this. And then it's the same. I mean, we get, when we take this expected value of x beta alpha, we get so we take this expected value of x beta alpha. This is just the probability that x beta equals 1 divided by, and x alpha equals 1 divided by p alpha, and that cancels. So then this equals the sum over alpha. We have a p alpha squared plus the sum over beta not equal to alpha of the probability that x alpha equals 1 and x beta equals 1 minus, p alpha p beta minus the probability that x alpha equals 1 and x beta equals 1. Okay, that's what we have. And then once again, it's like, this is, well, it's the negative of the covariance, right? So this is minus covariance of x alpha, x beta. And then I need to add and subtract the diagonal term, right? Plus p alpha times 1 minus p alpha plus the variance of w. So that's what this ends up being. Put the diagonal term back in, I get minus the variance of w, sorry. Okay, but now what happens is I have P alpha minus P alpha squared, and that cancels with this P alpha. So now we get instead of getting the 2, we get the cancellation, and this just becomes lambda. Okay, and that's lambda to the variance of W, and then I had that prefactor of lambda inverse 1 that I've ignored, and so that's why this is written like this. When I multiply that back in, I get this minimum of 1 of lambda, and then 1 minus variance of W over. So we have to divide this whole thing by lambda to get to this term. Okay. It's the same as before. We just use this positivity and then, yeah, negativity, whatever. Let's be positive. Positive. All right. Okay, so so we've actually already used. So now we can, now once we have this, we can just use this. We just need to compute means and variances. Essentially, what we needed to do before, but it's even simpler looking. Okay, so the first example is the head-run example that we started with today. So remember, because we had this x beta alpha was either 0 because they were far enough apart, or it was negative of negative x beta, right? So that was less than or equal to 0. No, it's less than or equal to 0, and so that was an example. And so you can go back and we computed it from scratch. But if you just compute the mean and the variance and look at the bound you get, it's exactly what we did. Okay, it's all the same. Okay, another example is hypergeometric distribution. So you count the number. You have some number of balls in an urn, and then some of them are red and some of them are green, and you sample without replacement, and you look at the number of red ones you get. And there you look at the sequence of draws that you have, and you look at the ith one. You write the indicator that you drew red on the ith draw, right? And those are exchangeable. It's a well-known fact. So they all have the same distribution, so you can compute the mean and the variance quite easily. And then how do you construct this size bias coupling? Well, it's like I choose one of the draws uniformly at random, and I have to force it equal to 1. So I have to put a red ball on the ith draw. But because of the exchangeability, that's just saying like I started with an extra red ball, and then that makes it less likely that other ones that I've so you have to it makes it less likely that you draw other ones like. So that's it. I don't want to do it in detail. It's a kind of a simple example. And then maybe a more interesting is the number of empty bins when allocating balls randomly. So let's do this example in some detail. So let's allocate K balls. Let's do it uniformly at random, but if you allocate them in different probabilities, the same thing we're doing is going to work. Uniformly random in n bins, and we'll let equal the number of empty bins. So we want to look at the number of empty bins. So xi is the indicator that bin I is empty after we've allocated the K balls, right? Okay, so that's what we have. And so again, there's some symmetry here. So, to construct these xji's, what do? Well, we want to force xi to be equal to 1. So we first allocate the balls, then we choose I uniformly at random, bin I. Given this bin I, we need to now set up the system so it has the distribution of the original system given the ith bin is empty. So what do? You take any balls that are in the ith bin and you just redistribute them, right? Okay. So we choose size bias. Choose bin I uniformly at random and empty it and distribute balls uniformly in the remaining bins. Well, once again, once we do that, all we've done is potentially add balls to other bins, and so the number of the indicator that bin J is isolated is now can only go down, right? Because I can put a ball into it. Yeah. Then xj I is the indicator that bin J is empty after the redistribution. Okay, and then clearly this is going to be, I had an empty bin and I threw a ball into it. It's no longer empty, and the indicator goes from 1 to 0, and that's all I can do. So this is clearly decreasing. Okay. So I should say, I don't know. I mean, maybe you don't care about these balls and bins problem. These balls and bin problems are, they actually come up in sort of statistical clinical trials and stuff like this. This sort of, doing these things, and people use them as null models and heuristics for stuff. As I said, you can change these probabilities. They don't have to be uniformly random. The construction is just the same. It's just the redistribution will be different. It won't be uniform anymore. You have to respect the probability of putting a ball in a bin. And then this is related to coupon collecting, which is something probably many of you know, is that if, it's a little bit of a different perspective, but how big does K have to be before this W is 0, right? Because W is 0 means you've collected all the coupons, right? Okay. Anyway, so this seems like a silly toy model, but actually it shows up in a lot of places, and analyzing it is quite useful in a number of settings. Okay. Okay, so now we can use this. So we just need to compute the mean. So what's the mean? Again, we have symmetry here. All of the bins are the same. So this is n times the probability xi equals 1. What's the probability xi equals 1? Well, I've allocated k balls, and I need them all to miss that bin, right? So the probability that one of them misses the bin is 1 minus 1 on n. This is chance that it goes in. And then I need to raise that to the power k. That's it. Yeah. And then for the variance, well, so we have the diagonal term, which is the same, just the Bernoulli variance. Okay. And then the cross terms, again, these are going to be all the same. And this covariance, it's now I have 2 bins, and what's the probability they're both empty? Minus the product of the probability each of them is empty, right? That's the covariance. So this is 1 minus 2 on n to the power k, minus 1 minus 1 on n to the power 2k. So this is the probability for 2 bins, the probability they're both empty after k balls, because this is the probability I missed them both, the power k, and then I have this. This is the probability each of them is empty multiplied together. Okay. So now you can see, I mean, sort of these two things are going to be close. The analysis here is maybe a little bit more delicate. So, but we still, because now I have this lambda here. When I divide by lambda, I get rid of that. That cancels with the 1. I have this term here, which we need to deal with. I have an n times 1 minus 1 on n to the k, and it's sort of, you have to estimate these things a little bit. So, so maybe I'll skip that in the interest of time. But I should just say, like, let me just have a little conclusion here. So if k equals n log n minus log alpha n for some alpha, then lambda equals alpha. So that's a little thing you can do. And whoops, sorry. This is the Poisson regime where you actually get convergence. But all the things I've said before are also true. The total variation distance, or W, and our Poisson is of order log n on n. Okay, so this is just a concrete example. But again, this is, you can write down what the bound is explicitly in terms of n and k here, and then do various analyses. Okay. Okay, good. So that's it for Poisson approximation. These are sort of specific references. As I said, a lot of what I talked about is in my notes here. For what I talked about and a lot more, you should really go to this this book, the Barbara Holst-Janssen book. Okay. Okay, so any questions about Poisson approximation before we move on to normal approximation?
So that means how we can come up with the operator, like if they want to try for other probability metrics, I think for time.
Oh, for the Poisson? Well, like I said, so the Poisson, it's okay. I mean, you have to do all that changes is you need to do the analysis of those solutions, and you can you can do it. But as I was saying before, it's like for the Poisson, somehow you compare Poisson to integer valued things, and typically the total variation distance is the strongest metric, and it's giving you the best rates anyway. So this is more important for normal approximation, which we'll talk about in a second. Oh yeah, you have a question?
Yeah, I was just wondering, so like, suppose we had like a distribution that had like, that would like mix discrete and continuous, like the discrete part and the continuous part. Would it be possible to like, in a sense, like combine Poisson and normals approximation into certain subsettings for like those kinds of distributions?
Well,
I imagine
I'm not
like,
sure.
for discrete stuff, if we really want to use Poisson, for continuous stuff, we really want to use it.
Yeah, I mean, I'm not sure what you mean by mixing. Like, if you mix you mean if you have an actual mixture or
If it's like a mixture, or like, either a mixture, or like, two, like you have like some parts continuous, some parts discrete, right? So like maybe like there's a discrete part and a continuous part.
Yeah, it is a good question. Just in general, like doing Stein's method for mixtures is a little difficult because in order to do these couplings and things, typically you have to sort of identify within the problem what's doing the mixing. So it's a little awkward. And if you can do that, then you should be able to develop something.
Combine both of them.
Yeah, because you can, like, if you give me a mixture distribution, I can write down a characterizing operator. It's basically the mixture of the two characterizing operators of what you're mixing over, or how many ever you're mixing over. But then somehow, if I want to bound that in an application, that mixing that I'm doing, the characterizing operator, I need to be able to identify that in the problem, right? So
The problem.
yeah. So there's some examples of that. So in these statistical physics models, like the low temperature Ising type models, basically you have two modes or whatever, and the limiting distribution is a mixture of normals over those modes, and you can identify which mode you're in, because when you do the sample, you're either near this one or that one, and whichever one you're near, it's going to look normal conditioned to be near that mode. So you can then see the mixture in the problem in that way. But I mean, actually, that's something I've thought about in other settings. It's there's not a real good machinery for doing that in Stein's method. So even the problem that I mentioned, I'm not sure that there's a Stein's method version of that. Yeah, even though that's understood. Yeah, but that's a good question. Okay, other questions? No, okay. Now I need to, how do I do this? Stop share? No. Okay, let's try. No, not that one. Oh, I should say I put some problems, just a few problems for Poisson problems in this Dropbox folder. So you can take a look at those. You should be able to do them all. Sorry, can I get some help? I need to switch to the other slides here. I don't know. I somehow can't even get to the stranded in the Zoom. Oh, stop share. Great idea. This one right there. No, that one. Yeah. Great, thank you. Okay, so next topic, new talk. Fourth new talk. It's all new talks here. Okay, so all right. This slide's the same as the other one. This is just an overview of what we're doing. I'm not going to bother with it. So now we're going to talk about normal approximation. Okay, so just to introduce the kind of setup. I mean, I think now we know what we're doing here, but let's just make sure we're on the same page. So let's talk about the classical CLT. So we have x1, x2, these are IID random variables, their mean is 0, their variance is 1. We look at this normalized scaled sum, 1 on the square root of n times the sum of all these xi's. And the classical CLT says that this w converges to a standard normal as n tends to infinity. And what that means is that the CDF of this Wn converges to the CDF of the normal pointwise and actually uniformly because of analytic considerations. Okay, good. So we all know this, right? Good, yeah, all right. Okay, so that's the first order thing. The next order thing is you might want a rate of convergence, and that's called the Berry-Essien theorem. So as I said, you have this uniform convergence of CDFs, and you want to know what the rate of convergence. So the Berry-Essien theorem says in the same setting, we can actually get a uniform rate of convergence, and the differences of the CDF on the left-hand side, I could take a sup over x because there's no x on the right-hand side. So it's a uniform bound on the rate of convergence, and it involves the third moment of the underlying IID random variables, and then it scales like square root of n. Okay. So that's the that's the basic thing. All right, and this is what we want to use Stein's method to get things like this, but where there's dependencies, or well, we should be able to do this. Okay. So as a first example, sorry, just get these notes to make sure I'm not missing anything critical here. Okay, CLT, the Berry-Essien theorem. All right, I nailed it. Okay, here's the thing I wanted to say. So the way you prove the Berry-Essien theorem in this setting is you can use, the classical proof is to use Fourier analysis, characteristic functions. It's still quite difficult because you have to use these very clever smoothing arguments. That has a bit to do with the metric here. That's a very non-smooth metric that we're comparing these probabilities in. But once you don't have independence of the sum-ins, Fourier methods are more difficult to use. You can still prove things like this, assuming various dependency structures, but there's still other situations where we might want to use Stein's method. So here's an example where Stein's method is going to be very useful. We already talked a little bit about this. Essentially, local dependence, but I'm going to strengthen this a little bit to the dependency graph. So this is an example where we're going to have dependence that's different than the Berry-Essien theorem, but we'll be able to prove a Berry-Essien type theorem. So let's say we have xn through xn, and they're random variables, and we say they have, this is a definition, we say they have a dependency graph G with vertices 1 through n, if the following holds. For any two disjoint subsets I1 through ik and j1 through jm of vertices, and those vertices have no edges between them in the graph G, then the collection of random variables indexed by the first vertex set is independent of the collection indexed by the second vertex set. So what that means is, so this is our dependency graph. Let me just draw a picture. So here's my, I1 through ik. Sure. Ik, here are these vertices. They're attached to some things. Maybe they're attached to each other. That's okay. All right, and so I have a graph, it looks something like this, that's okay. And then over here, I have sort of J1 through Jm, and they're also attached to various things. But whatever they're attached to, there's like a buffer between them. So there's no edges that go directly from my IKs to the JKs. And then what that means is that the random variables indexed by these will be independent of the random variables indexed by those. Okay, it's a quite strong situation. Okay, so so maybe we just do some examples. So read that. So what's an example? So there's maybe two illuminating examples. What if the random variables are independent? What's a dependency graph? Whoops. No edges. Okay, that's a great one. That's a great one because it's always a dependency graph, right? So that's my second illuminating example. So if we have, so the empty graph is always Oh, sorry, no, I'm sorry, so bad. No, correct, okay. Just, I had a, wrong, okay. Rewind 30 seconds, okay. If xi's are independent, then the empty graph is dependency graph. Right? Because all subsets are independent of all other subsets, right? Okay, now, is there another dependency graph for the independent case? I already said there is one, it's always a dependency graph. What's always a dependency graph? Well, okay, now for any, let's say I have n random variables that are generic, I can always find the dependency graph. What's the complete graph, right? The complete graph is always a dependency graph. Because then I don't have any disjoint subset, edge disjoint subsets, right? Okay, and so actually for independent random variables, actually any graph is a dependency graph. Because I can always add edges and it'll continue, once I have one dependency graph, I can always add edges and always get a dependency graph. Okay, now for the purposes of the central limit theorem, we have a dependency graph and we want to say when is this dependency graph, or when we, for a collection of random variables with some dependency graph, when is the sum close to a normal distribution? Well, we should be close to this, right, the empty graph. So somehow for dependency graph to be useful for the purpose of normal approximation, the heuristic is there shouldn't be too much dependence, there should not be too many edges, okay? So the point is that you want the minimal dependency graph or this, like the smallest dependency graph that you know you can have, but you can always add edges and you still have a dependency graph. So that's just to say this maybe wraps your mind around the definition, but heuristically you want to think of the dependency graph as really capturing the dependence between the random variables, and you want it to be as small as possible if you hope to have any normal approximation.
So basically, you have a simple dependency graph, or just the complete graph that they be independent effectively, or
the other, if the minimal was the empty graph, then they'd be independent.
the minimal of the empty graph, maybe.
Yeah. Okay, and so as an example, so as just a concrete example, we have this local dependence, which you've already seen in the head run example. Or let's say I have y1 through yn plus k minus 1, this sort of indexing. These are independent. And then we set xi to be equal to some function of yi through yi plus k minus 1. So we have some independent random variables that are sitting there. We put them in a line. You know, this is like the picture we had before, y1, y2, y3, and so on. And then let's say k is 2, and then x1 is a function of these two, and x2 is a function of these two, and x3 is a function of those two, right? So that's local dependence, like we saw with the head run example, is that x was a function of just a block of k of them, and then we slide around. And again, this is a very general statistic that's quite important in time series and stuff. They call this sliding window. Sometimes you have your underlying data is sort of randomly generated, but somehow there's some latent data that's randomly generated and independent, but what you're seeing is some collection of them over a finite period of time, okay? This is kind of a standard thing. So what's the dependency graph here? What's our minimal dependency graph here? So the dependency graph that we wouldn't want to use with k equals 2 is, well, this is vertex 1, this is vertex 2, 3, and 4. Well, if you look at this picture, it's quite simple. This is going to be x1 definitely depends on x2, so we need to put an edge between them. But it doesn't depend on x3, right? And so actually the dependency graph in this case looks like this. It doesn't depend on x3, it doesn't depend on x4, it doesn't depend on anything that's happening further. And I'm not taking this cyclic convention this time. This is why I've done it this way. Okay, and if k equals 3, so for k equals 3, it's kind of the same picture, but I have these adjacent dependents, but then I also have these second order type dependencies, right? And so on. I mean, you can generalize this quite easily. Okay. Okay, so, sorry, am I supposed to stop at 20 after? 20? Okay, great, thanks. All right, so we have 6 minutes. That's what I'm seeing on my watch. 8 minutes, wow, okay. I set my watch fast, so I'm not late to things, but and then also I end lectures early. Maybe that's good. All right. Okay, so we want to do Stein's method for things like this, sums of random variables that have some local dependent structure. We'll do Stein's method for other things and normal approximation. Okay, so in the Berry-Yassine theorem, the metric we're using is what's called the Kolmogorov or the Kolmogorov-Smirnov metric, where it compares the CDFs. For technical reasons, it's kind of a you can't avoid doing some smoothing in that metric, and so we're going to use a different metric. We're going to use the Wasserstein distance. So here I've used Wasserstein distance. It's misnamed. It should be the Kantorovich metric. But anyway, it's here. But if someone says Kantorovich, that's fine. Sometimes it's Kantorovich-Rubinstein. Whatever. These are all the same metric. But I'm using Wasserstein. It's a different W. I'll write Was on the board so my W's aren't too much the same. What is this Wasserstein metric? It's between two random variables, W and Z. It's the sup over all H Lipschitz functions, the expected value of H of W minus the expected value of H of Z. So again, this is like we talked about before. It's like I think of those as test functions, and I look at H of W, and if rich enough class of functions, expected value of H of W is close to the expected value of H of Z, you think their distributions will be close, okay? And in fact, Wasserstein distance does, if the Wasserstein distance goes to 0, you have weak convergence and convergence in means. And so it's a perfectly fine metric to use, but maybe you don't, it seems a little abstract. So what I want to do is show you that even if we're working the Wasserstein metric for normal approximation, it still says something about this much more natural Kolmogorov metric. Okay, so we have this proposition that I'm going to prove. Okay, and so this is a very standard kind of part of the reason I'm doing this. Is a very standard technique here called smoothing. You're working in a metric like this Kolmogorov metric. You can think of as being the test functions are indicators of half lines, and those functions are not very smooth. They have a jump, right? Whereas the Wasserstein is Lipschitz functions, which are smooth. And so you want to go from this one smooth function metric to a less rough one. What do? You do some mollifying or some regularizing, it's sometimes called. So let's just bound this thing. So what we want to do is, so the proof of this proposition is we're going to estimate the way to write this is equal to the expected value of the indicator, W is less than X, minus the expected value of the indicator, that Z is less than X. And so what we're going to do is we're going to approximate these indicators by Lipschitz functions. Okay, so that's the idea. So here's our indicator that this thing's less than or equal to X, like that. So this is X, this is 0, that's 1. And we're going to upper and lower bound this thing by a Lipschitz function. And here's the Lipschitz function. Let me get some colors. There are 2 Lipschitz functions that we're going to use. So one Lipschitz function looks like this. Okay, and another one looks like that. Okay, and I'll try to line these up a little bit. Okay, and this is X plus epsilon, and that's X minus epsilon, right? And so this function sits above our indicator, and this one sits below. Okay, they're not Lipschitz, but so let me call this one. Let's call this one H sub epsilon plus. Yeah, that's fine, and we'll call this one. We're fixing X, and then this one will be H epsilon minus. Okay, that's the idea. And then the key thing is that, well, H epsilon minus is less than or equal to the indicator. Dot less than or equal to X is less than or equal to H epsilon plus. Okay, and then the other key thing is 1 over epsilon H epsilon plus or minus is Lipschitz with Lipschitz constant 1. Okay, so those are Wasserstein type test functions. Okay, so then so let me just do so let's just do a quick calculation. So then what we have is the probability that W is less than or equal to X minus the probability this is less than or equal to the expected value of H epsilon plus of W minus the expected value of H epsilon minus of W. H epsilon plus of Z. Okay.
Yes, that should be sign of like
Oh, yeah. Thank you. So right. Yeah, okay, that's right. Yeah, the flips 1 on epsilon. We're going 1 in epsilon, 1 on epsilon. This is critical. Yes, thank you. Okay, so this is bounded by that, and I'm just going to add and subtract this H plus epsilon. So we get the expected value of H epsilon plus minus the indicator that is less than or equal to X. Let's write it like that. Okay, and then this thing is going to, this is not quite Lipschitz 1, so I can't really relate this to the Wasserstein, but if I multiply here by epsilon, I can. And then I divide the whole thing by 1 on epsilon. So let me just make a little bit more space, and I'll put the epsilons in blue so you can see them a little better. So that's fine. So this is less, so I've just added and subtracted this.
One of them.
No. This, because this is upper bounded by this, and this one just add subtract. Yeah. That's the key thing. Okay. So now this thing is less than the numerator here. This is less than or equal to 1 on epsilon times the Wasserstein distance. Okay, try this side. Okay. So that's less than or equal because this is a Lipschitz function. I'm comparing the expectations, the Lipschitz functions. And for the Wasserstein distance, it's the soup over all such Lipschitz functions of the difference of the expectations. And so this is one such thing. Okay. And for the bottom, what have I done here? H epsilon plus minus this indicator is just the function. So H epsilon plus minus the indicator. What does this thing look like? It's equal, they're equal up to X. And then it just looks like that. Right? That's all that's left. They're equal here, they're equal up here. I just get this thing, this function that looks like that. So this is 1 and this is 0. Okay, and so then this is less than or equal to, the integral over this line against the density of Z. So we're assuming that Z has a density that's bounded by C. Okay, I'll call this thing, this line, I'm not gonna write a formula for it, times the density of Z. Okay. And then we're basically done here. Let me just finish this thing. But this thing is bounded by C. This density is bounded by C. And then this integral of the line is just the area of that triangle, right? Which is epsilon on 2. Right? It's a triangle with base epsilon and height 1. Okay, so then altogether we get that the probability W less than or equal to X minus the probability Z is less than or equal to X is less than or equal to the Wasserstein distance between W and Z over epsilon plus C epsilon over 2. And now you just balance, that's true for every epsilon bigger than 0, and so we just balance it, and so we just choose epsilon equal to square root of the Wasserstein over 2C. Okay, so we choose times 2 divided by C. Okay, and then you'll get 2 times this thing. All right. And that'll give you this, that'll give you what's on the right-hand side. Sorry, the square root goes all the way down. So you just set the terms equal. You want them to be the same size. Okay, that's the upper bound. The lower bound's the same. You just use this h epsilon minus. So you lower bound this thing and then add and subtract for the h minus, and you get the same. You'll get the same inequality. Okay. Sorry, I really went over there. I'll stop here. So now we'll do everything in the Wasserstein distance, and that's what we'll pick up. When? Thursday? Thursday. Okay. Yeah. Thanks. Yeah.
Is there any algorithm that is spectral? You could take your graph with least number of features.
Well, that's a great question. It's not clear it's like linearly ordered or anything like that. So is there a minimal one? I think probably not. Actually, you can probably come up with funny examples where.
But there could be minimum difference, right? Because n vertices are.
Yeah. Oh, I see what you're saying. Is okay, minimum number of edges. Okay, the thing we're interested in is the minimal degree. Yeah, sure. There'll be many, and then there'll be one with a minimal degree. But no, I don't know of any. Yeah, it's a problem because it's like you add one edge and then somehow maybe you've chosen the wrong thing that cascades some dependency through, right? So yeah, it's not obvious to me how to do it.
With gas, then you probably get like a polynomial type thing to it would probably be like academic, you could choose that something where like.
Well, it's hard because pairwise independence is not the same as mutual, so it's not. I haven't thought about it. In most problems, you're lucky if you find one. So yeah.
Or maybe we could like get something that's like close to a dependency graph, maybe not a very dependency graph, but like it's like almost a dependency graph. It's going to be like like the collection of like different subsets that actually be like a dependency relation would be like very small or something like that.
Maybe. Right now? Like everybody or just me? Super. What are you? It's looking at me too. Just in case someone has a question. Then I'll share. Okay.
Whereas they should not have asked the question.
So in the last, quality is two for three border time or two other time distance also. Metric.
Oh, that's a good question. Let's see, so. Not, I can't say it's not true, but this won't work, I would say. So P Wasserstein is, so when you say P Wasserstein, you want the infimum of couplings. Okay, yeah. So something will work because there's another, I did this proof, this is a more general thing, but once you have a coupling, so what you can do here is, I mean, am I gonna be able to do this? But let me try. So you can sort of, there's another argument in this case. It doesn't work more generally necessarily, but in this case, there's another argument. So I have a coupling that's like, so yeah, I mean, the basic thing is, I'm not gonna quite, maybe I won't quite get it right, but you know, you have this like, you know, you sort of look at like the probability W is less than or equal to X. I mean, okay. So you break these events like this thing and the distance. And then you have plus. Okay, so you have things that look like this. And then if W minus Z is less than epsilon, then somehow you should be able to relate this to like either W is less than or equal to X, or you know, plus X plus epsilon or something like this. This is not quite right. Z in like X plus epsilon, something like this. So there's some way to get to the same inequality. So I can compare this probability. This is probably not right if I'm just doing it on the fly, but this is equal to that. And then this is basically the probability W is less than or equal to X, or this thing has to be an X plus epsilon, something like this. Maybe I'm not quite doing it right. And then you have this inequality as well. So the difference between these two things is essentially this, which is bounded, this is less than or equal to epsilon times C in this case, because it's the probability in this epsilon interval. And then this thing is less than or equal to the expected, you know, what did you want, the pth moment of this or something, right? Yeah, this is less than or equal to the expected value of W, right? And then this is bounded by your Wasserstein P distance to the 1 over P or something like that, right? So now you need to balance terms, and so you can get something like this. Yeah. Sorry, this is the Wasserstein P distance to the P, right? Yeah, that's right. So then you can balance terms, and so you should get something, you know, you have less than or equal to epsilon C plus your Wasserstein P distance over epsilon to the P. And so somehow, what would you choose? You need to choose, you should get this to like the P over P minus one, or you can just set them equal and then, yeah, but I'm trying to, I think maybe you get P over, the Wasserstein to the P minus one over P or something. Sorry. So then this, I think this will give you something that's like of order, the Wasserstein P distance to the, one minus, no, P minus one over P. Something like this. So as P goes to infinity, you get something of the same order. I should have said that before, actually, with this normal is like the square root of the like where we had is this Kolmogorov distance was bounded by this order of the square root, and that's bad, right? Because if the Wasserstein is going to zero, you're taking the square root, you're making it bigger, and and typically they're of the same order, actually. So that inequality is not sharp, very standardly not sharp. But so I guess here you get something like this, and then as P becomes large, it actually gets closer to one, right? Yeah. So yeah, but so this is, there's another argument that looks like this. So the answer, I guess the answer is yes. As long as you have the coupling, you can do something like this. Yeah, I presented the other proof because it's like sometimes you go from a metric that doesn't have a coupling, and then you want to get to one of these Kolmogorov type metrics. Oh, I stand too close. Oh, it's this thing. Oh, I see. Okay. I just gotta get out of the way. So anyway, so then you have a metric that's not, doesn't have a coupling, then this argument doesn't work. So if you want to go from a smooth test function metric that doesn't come equipped with it, like doesn't automatically come with a coupling, then you can't do this argument. But for the coupling ones, you can always do something.
One multiple. So here, it's sign of time, which is that is one. You also have to make sure that external is external.
No. Just Lipschitz.
One.
Oh, Lip one, just Lipschitz, just one Lipschitz functions.
The function is not bounded.
The function doesn't have to be bounded, no. Yeah. Yeah, I mean, of course, so then, yeah, I mean, another thing about the Wasserstein is it only applies to random variables that have a finite mean because, right, I can just take a Lipschitz function is the identity. So I need to be able to take expectations against things that are growing linearly, so it must have a finite mean.
People like me about things much good example like on things. Like inside like maybe one and then that's like
Yeah. So there's this bounded Wasserstein or what do they call it? Fourier. They have some other fancy name where it's functions that are both bounded and Lipschitz. Those are the test functions. Yeah. That will also imply weak convergence, the convergence of that to zero. So it's fine to work in that metric, but you don't get the coupling.
Right. All right.
I'm curious about the sign method also applicable in stable CFT. So you have random variable, not the normal, but.
Yeah. It is. So people have done, so actually Christian Houdray at Georgia Tech, he has a few papers with this guy Benjamin Arat. So people have done the problem is as we'll see, like somehow when we're doing Stein's method in this continuous setting, you do some Taylor expansion, you get higher order moments. And so for stable laws, you don't have higher order moments. And so, there's a bunch of wrinkles on top of it, but the basic maneuvers sort of work, but the whole solving of the equation and how you bound it is, there's some extra machinery that you have to do. But yeah, so there's some, Li Hu Shu at the University of Macau, he has some work on that as well. Yeah.
Maybe later I can take the exact name.
Yeah. I can give you some.
Anyone?
Are there any comparisons between Wasserstein and total variation?
Are there any, let's see, Not really, like, so if you have because total variation is like looking at indicators of things, and so if the indicators can be very rough, like in the continuous setting. In the discrete setting, there is, because it's like the indicators are going to be Lipschitz with some constant that depends on how close the masses are, right? So like in the integer setting, actually the indicators are Lipschitz, because I go from 0 to 1 and 1 to 0 in a space of 1, and so it's a Lipschitz function. The worst you can do is change by 1 over a distance of 1. So it's do you know what I mean? Does this make sense? Let me just draw a picture. So like if I have like integers and I have a function on the integers, either 1, so this is like n plus 1, n plus 2, whatever, and it's either 1 or 0. I mean, it's still Lipschitz because it's like it's either constant in adjacent places or increasing on a line of 1, right? So that's fine. But if this was like 1 on n, let me not do that. So if this were like you know, alpha on some other lattice of a different length, so like this was alpha, and this is 2 alpha, and this is 3 alpha. Now the slopes of these things are like 1 on alpha, right? And so, but it'll still be Lipschitz with some scaling or something like that. So that's what you have to do. You just have to say to compare them. And so not really, I guess, is the the right answer. Yeah. Yeah.
More questions? Whenever we have a discrete distribution, then we take the total variation, like.
Wait, discrete with his, and comparing to discrete with the same support. Yeah, then it's very natural.
Like, when you like, here we are like dealing with normal or continuous random variables, then you are like, again shifting that in, water time, right?
Yeah.
So, and always like for continuous distribution, we always use this water time too.
Well, yeah, I mean, I would say if the supports don't match, you just can't use the total variation distance, because the total variation distance, you know, if they're mutually singular, then the total variation distance is 1. So because it's the sup over the probability one random variables in some set, and the difference of the probability of the other random variables in that set. So if their supports are totally different, I can choose that set to just be the support of 1. And for one random variable, the probability of being in support is 1. For the other one, it's 0, and the total variation distance is 1. So you have no hope. So even for the central limit theorem, if I have the binomial distribution centered and scaled, and I compare it to the normal, total variation distance between those two things is 1. So it's not meaningful. So you just have to use a different metric. So if you have distributions that have the same support, then well, or that are, you know, that are mutually absolutely continuous, then you know, equivalent measures, then total variation is a natural thing to use. I mean, it may still not be appropriate because it's quite a strong metric and it's difficult to bound, but that's the setting where you would use it. And then otherwise, yeah, you want to use Kolmogorov, this, you know, look at the difference of intervals or half lines, or you use the Wasserstein, and these are just kind of the ones that people like to use, you know. Yeah.
What about this characterizing operator? Is there one for the normal?
Yeah. So we're getting there. That's yeah. That's like the next slide. Yeah. We'll do the Stein's method. Yeah. On Thursday. So, yeah. Sorry. Say again.
Wasserstein WP, I mean, is P strictly greater than 1?
No. P can be equal to 1. Yeah.
Is there any, I mean, format that is greater than 1, like equal?
Well, okay, yeah. So right. So doing P. Okay. So the question was, what about if we want to do the Wasserstein? So there's this Wasserstein P distance, which is okay. I mean, we'll have to say a bunch of things. So another definition of the Wasserstein, and this is related to an exercise you'll have. So this Wasserstein, I'm going to write it as the Wasserstein 1 distance, but this is what I mean between W and Z. This is the expected, this is the infimum over all couplings of W and Z of the distance between W hat and Z hat, right? Okay, so that's the Wasserstein 1 distance, but now there's a Wasserstein P distance where we take the P moment norm for that thing, right? So this is, and as P increases, this becomes a stronger metric. So we're doing this P equals 1, and so the question is what happens when P is bigger than 1? So the problem is when P is not equal to 1, then you don't have this, we need to be able to write this as this, to do Stein's method, we need to be able to write this as this expected, the difference in the expectations against test functions. And that is only when P is 1 do you have that duality. So that's the problem there, yeah. So, and there has been some stuff using Stein's method for P is 2, and I think larger P, and there it's quite different techniques actually to do that. So you can do it, but it's different techniques, and then doing the bounding is a little bit more difficult. But so for example, for the high dimensional central limit theorem, where you're interested in both the dimension and the number of terms going to infinity, and you're trying to figure out how big can the dimension be, can the dimension go to infinity with the number of terms? Right, so usually some polynomial in the number of terms, like how big a polynomial. I think for the Wasserstein P metric, like some of the strongest results are using Stein's method actually. So yeah. So you're interested in the rate of convergence in the high dimensional central limit theorem and the Wasserstein P metric. How can the dimension go with the number of terms to infinity? I think some of the strongest ones are due to using Stein's method, but it's a little bit, it's a different approach than what I will talk about actually. Yeah.
In the Wasserstein distance, instead of taking all each one function, you took only those each one function, what was less than or equal to 1.
Mm-hmm.
That would do for our purposes, right? Because
Yeah, in terms of getting convergence, like weak convergence. Yeah, that's true. Yeah. So, but I mean, we'll see. We don't need it. Also, I'm not sure. Like in this is probably okay too, right? This argument actually works because this is now bounded by epsilon, right? Yeah, should be okay. Something like this should be okay. Yeah, so you can do that. You can, and it doesn't hurt. But like for what we're gonna do, it's okay just to use the Lipschitz functions. And then the other thing is, so when you do Wasserstein P, it's equal. This is an equality. So what's nice about bounding this Wasserstein distance, not the bounded Wasserstein, but this Wasserstein, is once I have a bound on that, I know I have a coupling that satisfies the expected distance between them is equal to that or less than or equal to that bound. So that's quite useful. Like, I mean, just in terms of interpretability and things like that, right?
yeah, the point is, if the expectation does not exist, you won't be.
Then you use this bounded Wasserstein distance. Gosh, there's another name. It's like right on the tip of it. It's like Fortet Morier or something like that. Sometimes I don't know. Sometimes people call it this other thing, but anyway, bounded Wasserstein I think is good enough. Yeah.
Well, one more question, last question.
There's also a Carathéodory distance.
Also a
Carathéodory distance.
Carathéodory distance. Okay, I don't know this one.
One last question. You can some rule that both of my
Sorry, say again.
Are there some terms to expect vector sums to be both of y numbers and normal? When are there rules that approximate
Rules. Yeah, rules of thumb. Yeah. So okay, so for Poisson approximation, it's like, so we were saying, it's really, you think you have, somehow you can represent your random variables as sum of trials, a sum of, trials. They don't have to be independent, but they shouldn't be too dependent. And the probability of any particular trial being 1, coming up success, it's basically zero, but on average, you actually get successes. Okay, now we're letting the mean go to infinity. When will it still be Poisson? It will be Poisson. Okay, this is the rule of thumb, so I'm just saying it like it's true, but it's not totally true. If the ratio of the mean and the variance 10 to 1. So it's like if if you have a random variable that sort of looks Poisson in this sum of independent or sum of Bernoulli's, and they're all sort of have small probabilities, but you have a mean and it's sort of going off to infinity, just look at the ratio of the variance and the mean. If that tends to 1, that's pretty good evidence it's going to be Poisson. If it doesn't tend to 1, that's even better evidence that it's not going to be Poisson. Okay, so that's, if you're trying to prove something's Poisson and you're not getting that ratio to 1, it's basically not going to be. There's pathological examples, but as I said, any even higher order like uniform integrability of second of the square of the thing, and then that will be actually true. Must be me. I have a pacemaker or something. Okay, so okay, so then that's for the Poisson, and then so now let's say the mean, you're in the Poisson setting, and the mean and the variance are going to infinity, but they're not tending, like the ratio is not tending to 1. You might think the normal might be a good approximation, especially if it's tending to something else. Okay, but then the normal is it's a bit wider. It's a bit more universality in some ways. So now for the normal, it's just you have a sum of random variables, and you just think they're not too dependent, and none of them are too dominant in the variance. Okay, so that's like this like Lindeberg-Feller condition, this kind of thing. So if one of them dominates in the variance, then you're going to see its distribution. It's not going to look normal, right? So as long as they're roughly independent, not too dependent, and none of them are dominating in the variance, then it should look normal. Okay, that's the rule of thumb. But not too dependent here is not so clear. And in the local dependence, that's one way to say not too dependent. But there's also sort of weak global dependence. We have symmetries where you'll also see normal approximation, even though it's like quite strongly, everybody's sort of really dependent on everyone else, but it's this sort of weak global dependence. That's a bit harder to characterize. But those are the rules of thumb, I would say. Yeah.
Okay, so this session we end. Thanks. Thank you.
All right. Thank you.
Yeah, I have to be pretty more short on the folder. So, hold it on. Hold it on. I'll do that.
So we have two talks in this session, two short talks. First one is by Atul Shekhar from TFR. We'll talk about probabilistic Tauberian theorem.
Okay, thank you, Abhishek, for introducing me.
And thank you to LPS organizers, Siva, Varun, Subhajit, and Keshav for giving me the opportunity to speak here. So I was thinking of what to speak, and since this is a short talk of around 20 minutes, I chose this topic, which is rather elementary. So yeah, so this is probabilistic Tauberian theorems. Not theorems, it's just one one result, theorem. And this is not a paper in itself. This is just a section in a joint work with Christoph Garba and Chin Chen. So this is going to be pretty elementary. So let me start with the history behind Tauberian theorem. So this is ancient history, but nevertheless, it is worthwhile to refresh our memories. So this starts with Abel's theorem. With if you have a power series, is the pointer working? Is the pointer here? So if you have a power series from a n x and x to the power n, and if your the series of a n converges, then you know that the parcel the limit of the power series as x tends to 1 minus also exists, and it is given by the same L. Now this in itself is an interesting result, but I mean it's not too powerful, so to say. The proof is rather so one can prove this very in a straightforward way. You just have to do Abel summation formula to get to this. But the more interesting direction is the Tauber's direction, which was proved by Tauber, which is a partial converse to this result. So if you have a power series, again previously, and if you assume certain condition on your coefficient, so n going to 0, so an is little o of 1 by n, and on top of that, if your limit exists as you approach x tends to 1, then you can conclude that the series is also convergent. So this is quite interesting. So somehow from the information about the power series, you are able to know the convergence or divergence of the series. Now, early mathematicians who had number theory with number theoretic motivations behind them, Littlewood and Hardy Littlewood, they kind of worked on this and managed to reduce the assumptions that or conditions that you need on the coefficient in order for the converse direction to work. So Littlewood was able to prove that if it is sufficient to assume an is bounded, and later Hardy and Littlewood together they were able to further reduce this condition. Just positivity is enough. No more. So moreover, not only they managed to relax the condition, but moreover they extended their result, which is nowadays known as the Hardy-Littlewood Tauberian theorem, which reads as follows. So if you have a coefficient like if you have a sequence of an non-negative numbers, and if your power series diverges like 1 by 1 minus x as you approach x tends to 1, then you can conclude that the series the partial sum of the sequence k from 0 to n or 1 to n 0 to n is going to be asymptotic to n. So this is quite an interesting conclusion which you can derive by observing the power series or behavior about the power series near its boundary. Now, as I said before, much of their motivation behind proving such results was derived from number theory. In particular, finding an elementary proof of prime number theorem. At that time, there were many proofs. There were already many proofs of prime number theorem. Many of them were using complex analytical techniques, and they wanted to find a proof which avoids using complex analytical techniques and contour integration and whatnot. So many of them were interested in finding elementary proof. The elementary proof doesn't mean simple. Elementary here just refers to not using the complex analytical method, just using a real analytical method. Yes, and yeah, of course, basically. And one of the many elementary proof of prime number theorem uses this Hardy-Littlewood Tauberian theorem as a key analytical tool, toolbox. Apart from, of course, you need number theoretic components, but in terms of analytical tools behind the carpet, this is the main player, so to say. There are many other elementary proofs as well, but this is one of the elementary proofs. Now, this was taken up in much generality by Karamata. Again, I'm doing a little bit of history. This is ancient history, but still, I think it is worthwhile to recall, refresh our memory about this. So this was taken up by Karamata, who set up the theory of regularly varying function and gave a new short proof of Achel-Tauberian theorem. And this framework really made it possible to push the Tauberian theorem to a different level. So in the language of Karamata, in the language of regularly varying function, nowadays what is known as Hardy-Littlewood Karamata Tauberian theorem, the previous theorem can be written as follows. So if you have a monotonic increasing function, and if you consider the Laplace transform, there's a Laplace transform of it, and if you have a number p greater than 0, then your Laplace transform is asymptotic to s to the power minus p up to some constant, if and only if your function itself has a particular asymptotic behavior. So, so again, from the information about the Laplace transform, you are able to conclude something interesting about the asymptotic behavior of f itself. Okay. Yes, absolutely. No, so s is going to 0, t is going to infinity. I should have written that here. S is going to 0, t is going to infinity. So thank you for pointing that out. I should have written it here. Now, it may feel like that this result is very different from what was previously written about Hardy-Littlewood Tauberian theorem, but it's pretty much the same, except this one is a continuous variant of what we saw previously. So if you plug in, if you have a sequence an, if you take ft to be the sum of an for n less than equal to t, then the Laplace transform is exactly like this series. And if you substitute x equals to e to the power minus s, what you get is exactly the power series. So it's pretty much the same. But except this is written in a new language, in the continuous language, and in the continuous language, it's very convenient to set up the theory of regularly varying function, and that has many advantages, so to say. And this is what Karamata had done. Now, you may ask, where does probability, so we are all probabilists here, so we would like to see some randomness. So where does probability come in picture? And if you view at these results, not from the number theory perspective, but view them as analytical tools, then it has a perspective of being applied in many different situations, and in particular in probability theory as well. So there are many contexts where such results find very good applications. I will just mention two situations, which is, one is when you are studying the domain of attraction problem for IID sums converging to normal or stable laws. For example, if you have an ID sequence, and if you take the sum, renormalized sum, it is known that it will converge either to a normal or a stable law. Then you want to know under what condition on the given under what condition on the law of the random variable you converge to a particular given normal or stable law. So there is the domain of attraction problem, and its solution it heavily uses the theory of regularly varying function, and in particular Tauberian theorems and several such results like that. So this is one context. Another context where, so the book of Feller is a very good reference if you are interested in taking a look here. And another context where the theory of regularly varying function find many application is the large deviation theory in the heavy tail regime, the non-Cramer setting. So when you have a heavy tail set, so random variables with heavy tails. So there is a nice paper by Klein and Singh. So I would highly recommend you to take a look there, and references therein. Okay. Now, when I said probabilistic Tauberian theorem, this is not what I had in mind. This should be more like Tauberian theorems with applications in probability. This is not really probabilistic Tauberian theorem. What I have in mind is something different. So, which should be more naturally called probabilistic Tauberian theorem, is the situation when you have your f itself to be random. So your function f is not deterministic, it is a random function. And situations like that can appear very naturally. For example, if you consider a point process, any point process, for example, if you have a point process like some delta xi with collections of points, these are random collections of points, then you can consider the level sets, which is ft, to be the number of particles less than equal to t. So that would be that would be an example of random monotonic function. You can also consider a weighted, so you put a weight on each point, so it's g of xi, indicator xi less than equal to t. So these are some examples which naturally appear, which are examples of random monotonic functions. Now, if you're asymptotic, so in the Tauberian statement of Tauberian theorem, there is an asymptotic relation. If your asymptotic relation is almost surely, so you have asymptotic relation almost sure, then you can apply the so-called already known Tauberian theorem, omega by omega. For each fixed omega, you apply the Tauberian theorem. And so that's not complicated. But here's the interesting question, is what if your, what if your asymptotic relations are in convergence in distribution or convergence in probability? Does the same result as corresponding statement mentioned in the Tauberian theorem hold if you replace your asymptotic relation by convergence in probability or convergence in distribution? Now, at this point, this may feel like it's a bit artificial or unmotivated, slightly abstract, but let me give you a concrete situation where this situation does appear, where you do have a random monotonic function and asymptotic relations are convergence in distribution, not almost surely. So this is a situation which we encountered when we were dealing with branching Brownian motion. So let me quickly define this model. So you start with one single particle at origin, and this particle starts performing Brownian motion, standard Brownian motion, and it waits till exponential time one time, at which point the particle dies and gives birth to two of its children, and both of its children perform the same dynamics as its parent. They both independently of each other starts performing Brownian motion, standard Brownian motion. Again, after exponential time one, the particle dies and gives birth to two more particles, and this process continues. So at time t, you get some random number of particles. This is nt, and they will be located at some locations, and I'm naming their location as chi kt, where k runs from 1 to t. Okay, so this is the branching Brownian motion model. Now, it is interesting to study the so-called maximum particle. So if you consider the maximum particle, which is the topmost particle in this picture, this will be the topmost particle. So if you consider the topmost particle, then Bramson in early 1980s, he was able to prove that if I subtract this mt, which is given by root 2t minus 3 by 2 root 2 log t, then this difference converges in distribution to a randomly shifted. So this shift is also random, but okay, anyway, so shifted Gumbel distribution. Moreover, not only that, if recently in 2013, Argand, Beauvais, Kessler, Adecon, Jansi, Berestecki, and Brunet, they were able to prove that if you not only consider the maximum particle, but all those particles which are kind of at a bounded distance from the maximum particle. So if you consider all chi kt and shift it by this mt, which appears in the maximum particle, which determines the rate of at which maximum particle grows. If you subtract it, then this point process itself converges in distribution to a non-trivial point process. So here, by non-trivial, I mean two things. Non-trivial as in this is a non-empty, well-defined point process, and non-trivial as in also it's something which is very complicated to handle, to deal with. So here, this limiting object has a structure of what is called a randomly shifted decorated Poisson point process. So Poisson point process object is easy to study with, but there is a decoration on top of it, which is a complicated object, which makes it slightly difficult to study, or a complicated object to study. Anyway, so in an earlier work with Chen and Chin Chen and Christoph Garba, we were able to find a Markov process. So we were able to construct a Markov process on the space of point measures and realize this E infinity, the limiting object, as the unique invariant distribution modulo shifts of this Markov process. 5 minutes here. Good. Yes, so there is a very nice Markovian understanding of this extremal. These are called extremal point processes. So these are unique invariant measures of certain Markov process. And this Markov process can be easily described as follows: you take a point process, let each point evolve independently of each other under a Brownian motion, a branching Brownian motion. So each of these particles performs a branching Brownian motion independently of each other. You collect, at time t, you collect all the points, shift it by root 2t downwards, and what you get is a new collection of point process. And you can show that this is a Markovian system. And this Markovian system has only unique invariant up to modulo shift. The unique invariant measure is given by this object E infinity. Now, not only that, in a follow-up work, we also analyzed the domain of attraction problem in this setting. So the problem is for which starting states you actually converge to the invariant state. So for which point process your theta t converges in distribution to the invariant measure. So here we surprisingly found this cute little full characterization, complete characterization. Your theta is in the domain of attraction if and only if it satisfies this asymptotic relation. So 1 by t to the power 3 integral e to the power minus x square by 2t x e to the power minus root 2x theta dx converges in distribution. This is the key point that I want to make. It's an asymptotic relation in distribution here to some random variable. Z is a random variable. Now, if I plug in s equals to 1 by 2t, and if I write this as d of some random monotonic function f of x square, then this condition translates into exactly what appears in the Tauberian theorem. So s to the power 3 by 2, 0 to infinity, to the Laplace transform converges in distribution to this random variable. So that was quite neat. So this is a very neat full characterization of the domain of attraction. Now, this is the situation that I wanted to advertise. So to say that you do have a situation where you have random monotonic function, but you don't have almost sure asymptotic relation. You have asymptotic relation in the distribution itself, only in distribution. Now, coming back to the question that I raised, what can I say about Tauberian theorem in this context? Are these two really equivalent as you expected to be? Now, here it's almost the case, but there is a little caveat. The caveat is that this here, when you have convergence in distribution, asymptotic relation in distribution, it does not imply the tightness of the ratio here. In the deterministic setting, if you assume the asymptotic relation it implies the boundedness of the ratio of this left-hand side and right-hand side here. So that is only in the deterministic setting. In the random setting, that fails to happen. But except for that caveat, everything goes through. So the story is pretty much the same. And we were able to kind of prove this property. This should not be called a theorem, but again, as I said, this is a section. So this is done in the same paper where we studied the domain of attraction, and we were able to prove that you have, for a random monotonic increasing function, you have convergence in distribution of like that, if and only if you have the asymptotic relation. Again, s here is going to 0, x is here going to infinity. So you have this asymptotic relation and you have tightness, okay? And there is no substitute. So the tightness, you cannot really simplify this condition any further. So this is hard to simplify. In particular situations, you can come up with various conditions which allows you to verify or check this tightness condition. But I mean, as far as simplification goes, this is where this is the neatest way of the neatest possible way of writing this corresponding Tauberian theorem. Okay, so this is more or less what I had in mind. So this is the probabilistic Tauberian theorem. Now let me quickly finish just by giving just one very neat application of what follows. By considering since this is an invariant measure, you naturally have that E infinity is going to be in the domain of attraction of itself, which is because it's invariant. And you get for free by applying this Tauberian theorem that the ratio of 1 by y cubed in this integral converges in distribution to some random variable z. Now, as I said, this is a complicated object. So if you try to prove this directly by hand, this is going to be slightly tricky. So you need to develop some tool. But from this route, you can actually get this result for free. So you don't have to work any harder. So similar results, even better. So recently, they have managed to prove even better results. Were also obtained by Lisa Hartung, Cortines, Luidor, and Tianqi Wu. But yeah, so their proof is completely different than what we do here. Okay, so that's all I wanted to say. So I will finish here. Thank you for your attention. And I urge the students to find probabilistic counterparts of other Tauberian theorems.
Stop time, we'll go to the next step.
Okay. Yeah. Okay. Yeah. Thank you.
Maybe when we like take up, maybe we can take one question. I'll set up your answer.
Yes. I cannot. Can you say that again? Yeah. Yeah. Why that? Oh, that is. I mean, so if you have a collection of. So if you consider a family of independent random variables, you can also consider the similar things. In that case, your MT is root 2t minus 1 by 2 root 2. So you have a different constant in front of log, so to say. And so the convergence to Gumbel distribution is pretty much, so this is the extreme value statistics, as many of us are familiar with. But in this case, 3 by 2 root 2 is very specific to branching Brownian motion. So there is something called entropic repulsion that is related to this. So it's hard to explain. So, but I can explain you. Since we are from the same institute, I can catch him later and feed the information. Okay.
Thank you. So for the next talk, you will be focused on
Yeah, sure. Thanks, everyone. Is this the? Sorry, how do I use this? I'm sorry, I'm not sure. Like, can you just show me once? Okay. I don't know.
what happened? It changed our video.
Maybe that's for going back. Everyone for this opportunity. I'm going to talk about really this is an elephant random walk model or a reinforced random walk model, and the motivation of this being a nice model for market economics, especially in an oligopolistic market, actually comes from listening to one of Professor Krishna Molik's talks. So I thank him for that. So the idea is, the motivation is that, let's say that there are two companies, C1 and C2, and they release two different products, but serving the same purpose into the market at the same time. And people initially are not really aware of the underlying qualities of the product. So we want to develop a model where people base their choices of which products to buy on peer review. So let's say that the first few customers, they have nobody to ask, so they just kind of make an IID selection of products for themselves. But then from the n plus first customer onward, where like n is greater than or equal to some capital N, this capital N is fixed a priori. So the n plus first customer is going to select a sample of k customers from the past, and we assume that they are choosing the sample uniformly at random, and then notes down the choices made by the sampled customers. And then, of course, they will base their decision on the responses they receive from the sample. The sample may be drawn with or without replacement. For the sake of time, I will just focus on with replacement for this talk, but the actual work contains both of the situations. We treat both of them. Oh, I forgot to say that this is a work with my now graduated PhD student, Urchi Roy, who is an IIM CODE-IIT. Another variation that we take into account is that the sample size k could remain fixed as n varies, or it could be a function of n which increases as n increases. Of course, then we would have to make assumptions on at what rate k of n may be allowed to increase. So I'll come to that when we talk about the main results. So the n plus first customer will then ask these sample customers which products they chose, and then make a decision based on those responses. So far, no elephant random walk, but it becomes clear in a bit why this is a random walk where the walker remembers the whole past. So let's say that xi gives you the information about what choice the ith customer made. And for the sake of simplification, I'm assuming that every customer just selects one of two possible products. So xi is +1 if the ith customer has chosen P1, and it's xi is -1 if the ith customer chose P2. Let's say that these are the indices of the sampled customers chosen by the n plus first customer. So wherever I'm saying k, it could be k of n if it is varying with n. Let's say C plus is the number of sampled customers who chose P1. So you're looking at the sample and you're counting how many of those sampled customers chose P1. So more formally, so I write chi as an indicator random variable. So x sub un comma I, this is giving you the information as to which product the unith customer chose. Okay, so with this, once the n plus first customer has gotten this information, what Cn plus is, then they make their decision. It's still a random decision, and the decision happens as follows: the n plus first customer chooses product P1 with this probability, and they choose product P2 with this probability. Okay, and what are the new things here? So Cn plus over k, of course, is the proportion of sampled customers who chose P1. But there are two new things here. There is this constant P, which is between 0 and 1, and there is this function f. So I'll talk about those. F is a function that we assume maps from 0, 1 to 0, 1, and we'll make continuity assumptions and differentiability assumptions in the various results that we have. This is called a reinforcement function, probably also a replacement function if you see this from the perspective of earned processes. And the parameter P is referred to as the memory parameter or the self-excitation parameter. Probably also has other names in physics that I'm not aware of. Actually, this boils down to the original elephant random walk when you consider the sample size k to be equal to 1. So in the original elephant random walk, the n plus first customer just selects one customer from the past and then asks them what choice they made. And then base the decision, but without this f involved. In other words, basically, if you choose f such that f of 0 is 0 and f of 1 is 1, then you get back the original elephant random walk. So there actually this you will get xn plus 1 is 1 with probability p, and xn plus 1 is minus 1 with probability 1 minus p, provided that the sample customer selected p1. Okay, so you agree with probability p and disagree with probability 1 minus p in the original walk. Okay, so so this would be the n plus first step of the walk that we are considering. So we'll be interested in the position of the walker. So that is given by this sum, Sn, summation running from 1 through n xi. And we are interested in understanding if Sn over n converges. So I first talk about the almost sure convergence results. Then I'll give time permitting, I'll give some idea about the distributional convergence as well. So recall the function f, the replacement or the reinforcement function that I defined in the previous slide. I define this function g, which is basically, or it arises naturally from f. When we do the analysis, this is a very natural way in which g arises, both from f and the memory parameter p. So this is the first result. We are considering p in open 0, 1. So 0 and 1 are not really interesting values. And why do we exclude half? Because if you go back and look at the way we make the decision, xn plus 1, if you take p to be equal to half, you basically get back the simple symmetric rank. So it's not interesting. So we consider p in this domain. For this result, we are considering that a sample has been drawn with replacement and is of a fixed sample size k. We define this polynomial capital H, which actually takes, it's from -1 to -1, defined like this. So this function g is the same function that I have defined here. If this function capital H has a unique fixed point, x star in -1, 1, in fact, it can be shown that, which I also talk about in the next slide, when p is in this domain, this x star must lie in the open interval -1, 1. Then the sequence Sn over n converges almost surely to x star. So a little bit of discussion about what sort of functions do satisfy this or do satisfy the criteria stated in the previous theorem. So the function capital H can be shown to have at least one fixed point in -1, 1. Either you can show this using Brouwer's fixed point theorem, or you can simply show that at -1, capital H lies below y equal to x. At +1, it lies above y equal to x. So there must be at least one intersection happening in between. And when p is strictly between 0 and 1, all of the fixed points of capital H, this would be points, must actually lie within the open interval -1, 1. So for the previous theorem to work, we just need to come up with sufficient conditions that guarantee that capital H is going to have a unique fixed point in open -1, 1. And so a lot of different capital H will satisfy this criterion. So if capital H is strictly decreasing, this works. because then it can only intersect y equal to x, which is an increasing function, at most once, and it will be actually precisely once between -1 and 1. So this is, for instance, so of course, capital H is something we manufactured from the replacement function f and the parameter p. So if you would like to give conditions that actually come directly from the function f and the parameter p, then one of the ways to do it is just say that if p is between 0.5 and 1, and this inequality is true for all I in this notation simply means 1 through k, with at least one strict inequality. So there is at least one I for which this inequality is strict. If you have p between 0 and 0.5, and you have the opposite inequality being true for all I in 1 through k, with again at least one strict inequality, then this is in short. Similarly, if H is either strictly convex or strictly concave throughout -1 and 1, again, this is the condition of the previous theorem is true, because again, H is below y equal to x at -1, above y equal to x at +1. If it is strictly convex or strictly concave, it can intersect the y equal to x line at most twice. And in this particular case, it will be exactly once. So this is, for instance, ensured either this inequality being true for each j in this range with at least one strict inequality, or the opposite inequality being true, because you can either work with strictly convex or with strictly concave. So either of them, but you have to stick to one of them. So one of them has to happen for all of the j's. Okay. Another option is if H is a contraction. So one way to ensure that is simply having P in this range. So contraction would again ensure that it has a unique fixed point in -1, 1. The second almost shear convergence result, we are going to consider again sampling with replacement, but now the sample size is increasing in n. So for that, in order to state the result, I would need to talk about something called the modulus of continuity, which you generally define for continuous functions, as the name kind of suggests. And it's defined like this: for any function capital F on a given domain D and any constant delta positive. This is how the modulus of continuity of capital F with respect to delta is defined. So once again, we are interested in P strictly between 0, 1 and eliminating the P equal to 0.5 scenario. The sample is now drawn with replacement and is of size k of n, which increases with n. And the function g that we defined earlier, so g of x is p times f of x plus 1 minus p times 1 minus f of x. This function has a unique fixed point, say x star in 0, 1. And then all of these are really a bunch of growth conditions. So k of x has to satisfy certain growth conditions. Why does it need to do that? So this is where I need to show a little bit about how we prove these things. So remember that this is the position of the walker at time n+1. The way we write this is as follows. Okay, so this is the n+1st step. Okay, and now this you can this is the information, the sigma field up to and including time step n. Now this thing, if you write this as epsilon n+1, you can see that this becomes a martingale difference sequence. And this thing, this would be some function of Sn over n. So you write that as, let's say, because of the growing k of n, because k of n varies, you actually have this thing, a function, the functional form of which depends on n. Okay, so you have a representation like this. This is a stochastic approximation process, and this is the sequence of functions we need to analyze. So for us to be able to do anything with this, we actually require that this thing has to converge. Otherwise, you cannot deal with it. Okay. And what turns out for us, what happens is that we actually get a subsequence of Bernstein polynomials converging to a certain function. Okay. So to deal with this, so in the usual stochastic approximation, we just have a single function, h of xn over n, not a sequence of functions. To deal with the sequence of functions, we need some more assumptions, and those are given by these growth conditions on K of n. Okay, so not going any further into this, but as you can see, we tried to consider different classes of f. So when f is just continuous, you have this kind of a growth condition. When f is Holder continuous with an exponent which is between 0 and 1, you have something else, and so on. Okay, so here in these two, you have differentiable and twice continuously differentiable, etc. So the final conclusion is that if all of these things are true, then Sn over n converges almost surely, but now it's to 2x star minus 1, where x star is the unique fixed point of G. I just wanted to go through some of the criteria, some of the classes of functions f for G, for which you do have a guaranteed unique fixed point. So again, these are similar to what we saw previously. Either f is strictly decreasing when p is between half and 1, or f is strictly increasing when p is between 0 and half. That will do. When f is twice continuously differentiable and f is either strictly convex throughout 0, 1 or strictly concave throughout 0, 1, again, a unique fixed point of G is guaranteed. And if f is Lipschitz with the Lipschitz constant C satisfying this inequality, you can actually say that G becomes a contraction. Okay, so it has a unique fixed point. So this is the, second last slide. So quickly want to go over convergence and distribution. So this was once again, this we introduced previously, this function. So once again, we are first focusing on the case where the sample is drawn with replacement and is of constant size k. And again, capital H is assumed to have a unique fixed point x star in minus 1, 1. Then if we set tau to be equal to 1 minus capital H prime x star, this is a polynomial, so it's differentiable. It can also be shown that tau in that case would be strictly positive. Then we have these convergence results. So there are three regimes: tau bigger than half, tau equal to half, and tau less than half. Okay, so for tau less than half, you actually have an almost sure convergence. And since we are almost out of time, so I'll just quickly mention that when the sample is drawn with replacement, but of size k of n, where again k of n is growing with n. So in this particular case, we just assume f to be in C2 for the sake of simplicity. Otherwise, the conditions become hard to state. That's all. Even then, it can be found. So here, G is assumed to have a unique fixed point. So previously it was capital H, now it's G. X star and 0, 1, and tau is set to be 1 minus G prime x star. So if you take f to be in C2, G is also in C2, so G prime x star is well defined. And we have a bunch of conditions. Again, these are all growth conditions on K of n, because you have to control the errors now carefully. And we have more errors than we had in the previous case where K was fixed. Then we have this result. Again, the regimes are very similar. And for tau less than half, we once again have convergence on surely. So I think I'll stop here if you have any questions. Thank you.
It's very similar to a noisy version of the majority border. You know, if the majority border
See, we make the assumption that f is like all kinds of nice smoothness assumptions are there. If you make it a majority, which has been analyzed, but I doubt has been analyzed rigorously, like this thing. So there are 3 papers by Simone Francini, and he does look at the majority function, not this nice f, but majority. But one of them is about large deviations. And the other one does state some results, but we couldn't really find any rigorous proof. I mean, we are still looking. So yeah, and I don't know like how one would go about using essay, because in essay you require all kinds of smoothness. So I don't know that yet. So yeah.
Two announcements, one is, that is, what is the camera?
All of the process in the camera photo group photograph. That's very important. I can't also get. The next thing is, we again split for lunch. People who went to the campus cafe, go there again. Who were PGH, go there again for today. We'll decide about Thursday later on. And people who didn't come yesterday, just come with me PGH. But for that,
Okay, so I will start by proving the result we ended up with at the last time. So recall that we defined the operator norm or the spectral norm of a tensor. So tau is a order R tensor. And the elements are sub-Gaussian random variables, independent sub-Gaussian random variables. So before that, let me just define the injective norm. Okay, so this is just the, you take the multilinear functional and optimize over the product of unit spheres. So like this. Right. So by the way, I have given you some exercise problems. It's uploaded in the Dropbox, and in one of them, you're supposed to find natural definition of singular values as singular vectors, and then this, with that definition, this also happens to be the largest singular value, just like in the case of matrices. Okay. So we'll assume that tau I1 to the entries are sub-Gaussian, zero means sub-Gaussian, with a common parameter sigma square. And independent. Okay. So then the result that we want to prove is how large is this operator norm. Yeah, I mean, I should not call it a theorem, maybe some propositions. We'll show that with high probability. This is square root log R of the dimensions of the modes. Okay, this is what you want to prove. And just as an aside, I mentioned it last time. If you have a random matrix, we know that square root n is the right order, right? If, for instance, you have a matrix that is R is 2, then it's known that the operator norm given by square root n converges almost surely to 2. Yeah, so we'll assume that all of them have the same mean 0 and variance sigma squared, then it converges almost surely to 2 times sigma. Okay. So square root n is the right order. Where?
Formula position, we should have a root log with R equal to 2.
Root log 2.
Don't have like a root now.
Here, I mean, sorry, I should put a big O here. I don't care about the constant. Yeah, yeah. Yeah, I don't care about the constant. In fact, these dependencies over R, they are not sharp. Okay. In fact, I'll not be able to prove this, but I will state one result where it is shown that if you take IID Gaussian entries in this setting, then again the operator norm as defined by square root n converges to some limit, almost sure. Okay. Yes.
One takes two overall mixed tensors.
Yeah, overall mixed tensors.
The maximum aimed at pure tensor.
Not necessarily. If it's symmetric, then yes, you can take
The monster.
the constant. Yes, the constant doesn't depend on R. This R dependence I have included it here. Also not an n, of course. Yeah. So the other parameters are already written here, but these dependence are not sharp. And yeah, unfortunately, so this is no need great generality. We don't need the things to be Gaussian, right? This is known for. So this is a result due to Bai and Yin. If you know finite fourth moments, then you can prove a convergence result like that for matrices only. In the case of tensors, it is only known for Gaussian matrices. Okay, an almost sure result of this form. To supplement that, I think last time I mentioned this as an exercise, but I plan to do it here. We show that that's actually the right order, at least the square root n part of it. Okay. So in fact, one can show that this is bigger than or equal to some p square root n with high probability. So what is n? Last time I think, so the example that I will give, I'll just take all of them to be equal actually. NR. Hmm?
Because like over there, it's like summation of the end.
Yeah, but R is like a constant. Yeah, and yeah, and we are essentially going to consider the proportional regime where all the n's are proportional to each other. That regime, this is like R. Yes. Yes.
The same order.
Which case you mean this? So I'm taking supreme over mixed tensors, right?
So mixed meaning one could take linear combinations of pure.
Not necessarily then. Yeah. Why, unless you constrain it in some way by the norm, why would you get the same thing? Right. So you, yeah. I mean, you have to constrain it in some way. So that's like a rank one matrix. So that you can think of as a pure matrix, and mixed tensors are linear combinations of those. The example that I'll give is only in the symmetry case. So I'll basically cheat. I will show that there is a matrix model where I know what the lower bound looks like, and the operator norm is lower bounded by the operator norm of the matrix model. So let's prove that result. That's not difficult. It's a simple covering argument. You probably Many of you have already seen it, but anyway, it's good to do it. So we have this supremum over a big space. What we'll do is we'll convert it to a supremum of finitely many random variables. So basically, we'll take epsilon nets for each of the spheres, and from each net we will find the relative of this guy, and then you essentially get a bunch of sub-Gaussian random variables. You take their maxima, right, and perform an union bound. That's the basic argument. Okay, so let me just follow my notation here. So so in line with the exercises I had given, so let me just recall some exercises. So here is one quick lemma. Suppose I think I wrote down last time. So suppose x1 and x2 are independent sub-Gaussian sigma 1 square and sub-Gaussian sigma 2 square random variables. Then you know that a1x1 plus a2x2 that is sub-Gaussian with variance proxy a1 square sigma 1 square a2 square sigma 2 square. So then can you tell me what would be the sub-Gaussianity parameter of this object, this linear form? It would be sub-Gaussian. It's a linear combination of bunch of independent sub-Gaussians. Yeah, so let's write down the expression for it. Start, this is sum over tau t by r. Yes. So I assume that all of them are sub-Gaussian with the same parameter sigma square, right? This is going to be sub-Gaussian with parameter what is this? Product of all the norms, right? And they're all ones, square norms. Okay, so they are all of those are also sub-Gaussian sigma square. Are. Okay. Okay, so I'll pick a bunch of epsilon nets. So nj, let nj be an epsilon net for is to the j minus 1, nj minus 1. You all know what an epsilon net is. It's basically a bunch of points such that any point of that sphere is epsilon close to some member of those sets. It's a finite set, right? And sorry. I meant this basically. I meant this. Sorry. Thanks. Thanks, Karan. So this is subgaussian for every choice of x, right?
Well, even like from the bottom, X1 R was like.
Which one?
Left-hand board. Right-hand color.
Yes.
X1.
I keep making the same, indexing issue, right? Yes. Yeah, probably it's better to write the one here, then I will not forget. Yeah. Anyway.
So, like, this
I'm not, yeah, go ahead.
each of those would be like, sub-Gaussian sigma squared, then would the sum be like sub-Gaussian n to the r sigma squared? So like, because I1 and IR vary like from 1 to n, right?
I1 to IR will vary from 1 to n, yes.
Means that,
But then so I'm applying this result here, right? So you get all of the
yes, individually, the thing should be normal y.
yeah. So these are sub-Gaussian sigma square. So this is your coefficient. So you get all of this with sigma square and some, yeah, and that's just a product, right? And all of them are on the sphere. So
Yeah, I did individual products, but like the sum. Oh, okay, fine, you just find it. Fine.
the whole sum is a sum of sub-Gaussian variables, independent sub-Gaussian variables, right? So yeah, I am very bad with indices. Yeah, right. XRIR, yes. Yeah, so I'm very bad with indices. I can, so Krishananda taught us analysis 1 and he, or probability 1, but yeah, it was very analytic and and there were like these subsequential arguments with towers of four indices going on on notebook. So from that time onward, I am frightened by indices. Okay. Huh? Yeah, so let's take an epsilon net of the sphere, and I'll call let me just stick to my notation here, otherwise I'll make a mess of it. Okay, so for all xj, there is some element of the net such that right? Xj is epsilon close to Vj. That's the definition of a net, right? So the goal is to replace this swoop over an uncountable space over there to a swoop over the Cartesian products of these nets, right? I know that each of them are sub-Gaussian with parameter sigma square, each of these things. We have a bunch of sub-Gaussian sigma square variables over a finite set, so we can apply the result that we wrote down earlier for the maximum. So that's precisely what we are going to do. So before that, we need a continuity argument. So how close is this to the corresponding net counterpart? Okay, so I need an estimate on this. How close is this to the net counterpart? So any ideas? How should we bound this? I know that, so I have for each, so here x1 to xr are fixed, right? And then for each one of them, I have picked the element from the corresponding net, which is epsilon close to it. Right? So then how much do these differ?
You can do like a plus minus, but with the change coordinate vector.
Exactly. So you can do I can compare by coordinates. So let me just do a triangle inequality like that. So I'll just, in the first one, I'll just change x1 to v1, keep the rest fixed. Right? And you do it like this, and at the end you have maybe you have replaced everything but the last one. So v1 to yeah, please tell me if I'm making any mistakes with the indices. Maybe this is XR, right? I have just yeah, I've replaced everything but the last one. Okay, so I can do a sum like this, triangle inequality like this, and then how much is that?
Second one, I think you meant to change V1 X2 up to X1.
Thank you.
Yeah.
That looks fine, right? So each one of these terms, there is they only differ at one coordinate, right? So yeah. So again, can I write this?
Yeah.
Right. Each of them differ by at most this, and there are R copies of this. Right? Very good. And yeah, so this is an exercise. You do this by volume. So I have to avoid that. Okay. Okay. There are R terms. I am replacing one at a time. Okay. Yeah, okay, you're right. Probably I need a constant. So right. So you mean xi minus vi, you have to normalize so that it becomes on the sphere, right? And that's bounded by 2, so maybe I'll put a 2 there. Thanks. 2. Okay. Simple, show that I don't remember the constant, but I believe it is 2. Okay, you can cover the sphere by these many bulbs of radius epsilon. Okay. So let's now first get a bound on the expectation. Maybe it's interfering with my tablet. I don't know. Yeah. Sorry, I'm charged. Yeah, after the lunch, I must be. Right. So before that, maybe I'll write down one more line. So with that, I want to compare the supremum over that infinite set with the maximum over the product of the nets. So I think this is correct. Let's see. It could be nj minus 1, yeah, but it's fine. I mean, I'm being very lossy there. I don't care about the 1, right? Yeah, it probably should be nj minus 1, like it's thinking of a circle. Yeah.
Right.
Yeah. Very good. So And yeah. Right, so I know that I can replace each of these by a corresponding net version, which is here, with at most this error, right? So I can upper bound this by a soup over the net, right? Of the net version. Okay, up to this error. Right. So my tau and t are there isomorphic, so it's bothering me. Hence, we have proven this inequality that the operator norm is at most 1 by 1 minus 2r epsilon times the soup over the net. Okay. All right. So let's yeah, last time I gave you one exercise. So let me write that down here and apply that here. So so suppose you have a bunch of sub-Gaussian sigma square random variables. Right? Then not necessarily independent, then the maximum of them is at most, expected maximum of them is at most 2 sigma square log n. Okay. So what happens if I apply that to here? What is n? No, n is the number of sub-Gaussian random variables you have, right? How many? 2 over epsilon to the power nj minus 1 product of them, right? Very good. So yeah, and then I'll just write down, group the constants here. Sigma square log 2 over epsilon to the summation nj. That's the source of the summation nj coming from the entropy. Okay. So what is the right choice of epsilon? You have to pick epsilon suitably. So if you pick epsilon close to 1 over 2r, this will go blow up, right? So yeah, and you of course you don't want to pick epsilon to be close to 0 as well. Then this will blow up, right? So the right choice would be some fraction of 1 over r. Okay, so that this is both of these are controlled. So choose. So maybe 1 over 4r. That gives you that extra log r factor that you see in the. Right, and okay, so the high probability version I will leave as an exercise. So I'll give you the precise statement. So show that given eta positive with probability eta bigger than or probability bigger than or equal to 1 minus eta, the operator norm is less than 8 sigma square sum of a log 8r equal to 1 to r, and of course term accounting for the error probability. Okay, so this is just converting that to concentration amount. Any questions about this? Okay.
One can say, so that's a vector in R to the power of n1 plus nr.
You can write it as a vector, yes.
Say an arbitrary vector in that state.
Yes, yes. Yeah, but you're maximizing over a product of spheres here.
Suppose the maximizing over all vectors, non less than equal to non
In there, so that would be an upper bound on whatever we're considering. Yeah.
But would that give you the same asymptotics?
Not necessarily. We'll see some examples. So that is one technique of obtaining cheap upper bounds by unfolding the tensor into some flat matrix or a smaller order tensor and using this. And how you unfold that gives you a degree of freedom, and in different regimes you can update it. Okay. Let me prove this. Lower bound.
Also, the cleaner method, then you need a concentration instead of like power or next.
Yeah, you can use as a maximum bigger than something. You can use union bound, right? And then again the entropy will come. Okay, so yeah, so this is a nice trick. So what we'll do is now I'm far away from that. I'm just
Nothing possible for it.
or my charge is increasing over time. Yeah. Okay. To define a matrix, A, the ijth entry is given by the tensor. I'll keep the first two at ij and the rest would be ones. Okay. I'll pick one slice essentially. That's my matrix. Okay. So this is of course going to be smaller than a soup over a smaller set. I'll keep all the, I'm picking the first coordinate of each other axis, right? I'll just multiply with the E1 vector. Right? So this is a cheap trick. You instantly get a lower bound in terms of the operation of that matrix. right? But from you already know that if you have matrices, we know that if you scale by square root n, I go to constant, so you can from here you can say that. Very good. So now let me tell you what happens if I have Gaussian entries. I won't be able to prove it, but at least give you a flavor of what happens there. So people are familiar with Ising models, Ising models. Okay, let me define. Um, so you have let me define the general version anyway. So you have an hypergraph. We have already defined hypergraph. So you have the adjacency tensor. This is the indicator if this is an hyperedge. So at each of the vertices, you have a spin plus minus 1. Okay, so you have a spin configuration. So the hypergraph on n vertices, of course. So then on spin configurations, you can define a Gibbs measure by giving a energy to every spin. So the energy that will give is precisely that multilinear functional of the tensor. Okay? So sigma is a vector of plus minus ones, right? So in our notation, this would be just this. Right? This is a R uniform hypergraph. The hyperedges are all of size R. Okay. So this gives you a notion of an energy associated to this particular spin configuration. So these are spin configurations. And this is the energy associated to that spin configuration. Probably if you are a physicist, you will put a minus sign, but we will we don't care. Yeah, so maybe you have seen Ising models where you just have a graph, right? And then if there is an edge between I and j, the model will prefer spins which are alike, which are aligned, right? So this is a generalization of that, right? I'm allowing interaction between R many spins simultaneously. Okay. So this is called the R spin. Okay, so what is the probability measure? Of course, the probability measure is the Gibbs measure corresponding to this Hamiltonian. So I guess if I don't put a minus, then I will prefer high energy configuration. So let's put a minus at least there. Thanks. Yeah. So then this probability measure prefers configurations which are aligned across areas, right? And so this is a hypergraph generalization of that. Okay, so this is called an R-spin Ising model. So these Ising models, they model typically magnetic materials, but there are things that show glassy behavior, and for which what you do is you model them by making this random matrix, in fact, a random Gaussian matrix. So then the same model with this changed to a Gaussian random matrix gives you a spin glass. Okay. So since I'm talking about tensors, so Gaussian random tensor, I get what is called the spin glass. So now there is no preference to this type of alignment, the configurations which are globally aligned, right? Because okay, so this is analyzing this is also difficult. So what one can do is we can relax this spin configuration. So right now the spins are plus minus 1 valued. What we'll do is so since they're plus minus 1 valued and there are n of them, they lie on the sphere of size of radius n. We'll do a relaxation. We'll pretend that now my spins are living on the sphere of radius square root n. Right? That would give me a Gibbs measure on the sphere. Right? That's called the spherical R spin glass. Sigma is now on the unit sphere of radius square root n. Okay. Sphere of radius n. Okay. So this is called the spherical R spin glass. So you see what I have done. I have replaced these spins by the elements from that unit sphere, right? And now what configurations do I prefer? I would prefer essentially eigenvectors or singular vectors, right? Because my Hamiltonian is precisely that multilinear functional in the sigmas. So using this connection, so by the way, if these are Gaussian, then of course you can see that this is a Gaussian field. Indexed by the unit sphere. Right? So that allows, so this interpretation allows you to use results known for Gaussian fields, in particular things like Katz-Rice formulas for obtaining the number of critical points, for instance. See, critical points of that this form, they gave rise to our eigenvectors. Right? So using this connection, one can actually give an explicit asymptotic representation of the number of critical points of that Hamiltonian. Okay, so I'll write down because so we'll not prove it, but the interpretation that we get out of it is quite interesting. So so let me define. Okay, so one more thing, I think I will also put a normalization constant here into the R minus 1 over. Okay, so that's convenient because if you take this, you will see that the typical energy will be of order n, and that will scale with the entropy, which is like 2 to the power n. So in the exponential scale, it's like n. So to balance things, we'll put this normalization over here. Okay, this is just a normalization. If sorry. So in my notes, I think I have written there is no capital N. Little n is capital N. Yes. Glassy means you just like glass. So there are values of configuration. You know, there is no alignment as such. Like if you think of spins, so there are patches of plus signs and minus signs, etc. There is no global alignment. Very roughly, that's what it means. So it's meant to model the behavior of glass, but there is no alignment of the spins. Yes, any questions? I think I'll define it like this. So this is the number of critical points. So number of critical points inside a set B. I'll define what it is. Yes? Standard Gaussian is standard Gaussian. You can symmetrize because it's a form, right? So you can always find a symmetry. Critical points for which the critical values lie in the set B. Okay. So in fact, as per my normalization, as I said, this okay, sorry, I'll probably there is no capital N, everything is small n. So the normalization makes it so that the typical energy scales like n. Okay, so that's why I'm scaling. So give me any Borel subset, I'll just scale that set by n, and I'm counting how many critical values land in that set, right? Critical values, so you have that they satisfy this equation. Okay. So there is a very beautiful. Oh, by the way, so before I go to tensors, what would happen if I just take matrices? What are the critical values of that form? They are eigenvectors, right? Eigenvectors, a singular vector. So, and how many of them are there? How many critical points are there? So each eigenvector with plus minus one side, so 2n many, right? And these are the eigenvalues essentially. So this will essentially be representable as an integral with respect to the semicircle density in the limit, because in the limit the density of random matrix with that symmetry or without the symmetry, I'm looking at the form, so that converges to semicircle law, the bulk law. So the matrix case is very easy. There is a easy reduction to tensors, reduction to random matrix theory. Okay. But yeah, so I'll write down the formula. There is a very beautiful explicit formula, which is precisely an application of the Katz-Rice formula, which I'm not going to, for counting the number of weighted counter number of critical values. This formula is not very important, but after you have this formula, you can try to do an asymptotic analysis of it, and this gives rise to very nice limit results. I'll change every appearance of n and p. There is no p, p is r. Okay, that n. Very good. 2r, and here you integrate with respect to the density of the empirical spectral distribution of a GOV random matrix. Okay, so some density which converges to the semicircle law. So you have a very explicit formula for this expectation. So what does that give us? So by analyzing this, you can prove that expected number of critical values, for instance, does this look at this formula, does this ring a bell from what you have seen in the previous class? So I'm counting the number of critical values. So the Borel set is R here, so all critical values, right? And in the logarithmic scale, it's giving me the explicit R minus 1, R minus 1, the explicit rate of growth, right? So what are these critical values for our tensors? They are precisely the Z eigenvalues, right? We know that the total number of E eigenvalues, we have an explicit formula, right? And last time we saw that that grew like R minus 1 to the power n up to some constant. So there are some R minus 2, etc. there, but this was the order of growth. So this is the number of E eigenvalues if you allow complex eigenvectors and eigenvalues. And this is up to some polynomial factors giving you the rate of growth of the eigenvalues. How many on an average, of course, right? This is just the square root of that. Yes. Sorry, this expression, this is an exact identity. So I'm integrating over this set B. It's the scale set B. Yeah. Okay, so B is a set, Borel subset of R. And yeah. This technology gives you the number of Z eigenvalues asymptotically for yes. Okay, it's almost maybe we can stop now and take up.
Because you are not bothering about fastest.
Yeah.
Why this?
I think because no, right. So oh, you are right. So xi minus gi is less than or equal to epsilon. Yeah, that's already there. So 2 should not be there. Thank you. Thank you.
I did sometimes start learning and I just decided it's pointless to carry it. So it kept in my bag and I might as well get right now. But what do you do? After this whole thing. Oh, no, so this is good.
Keshav, when?
All is nice.
3 months ago. I had to organize.
Like,
Thank you. Yeah, so we basically know the correct exponent of the number of z eigenvalues on average. In fact, with that as an input and some more spin glass theory, you can also prove where the optimizer converges. So I think okay. So this converges to some negative number. It depends on R. You can give a inexplicit description of that, but I'll not attempt that. Okay, so because the entries are symmetric, that also gives you the behavior of the largest or the operator norm. Okay, I guess I don't know. So in probability, let's say. And this implies that the operator norm of scaled by square root n, that also converges in probability to Q0R. So by the way, so this was this critical point business was done in a work of Offenberg, Benarus, in 2011. All right. So the bound that we proved, they are, as you have seen, they are of the correct order, at least for sub-Gaussian tensors. But in many applications, you need RCT. The entries are sparsified, for instance, by some Bernoullis. So for such, these bounds are quite suboptimal. Okay? So let me write down a result which is valid for sparse tensors as well. And I will also allow variance profile. So P denotes probability tensor. That is, each entry is between 0 and 1. Yeah, I probably should write something like this into the. Yeah, these are not vector spaces, of course, but yeah. You know what I mean. The entries are between 0 and 1. Yeah. No, it's actually, you use the usual spin glass result to together with that to prove this. For the usual spin glass, +1, -1, I don't think it is known. It is only known for spherical spin glass. What I mean is that with that representation formula, plus the fact that for the usual spin glass, you have a description for the, so you have to do some asymptotic analysis there. You get an object. So that object has a description that is valid for usual spin glass as well as the spherical one. So that description is useful. If you use that together with That's called the Parisi formula. But anyway, so if you use that together with the description, you can derive this result, and the operator norm converges.
From there, at least it's order of
Order we already know, right? From that result. I mean, we don't know. If you allow me constants, I already know the order. It's square root n. Okay. Okay, and I'll take a tensor T, whose expectation is P. The elements are IID Bernoulli random, independent Bernoulli random variables, right? With elements from this probability tensor. So this follows Bernoulli PI1 IR, and they are independent. And denote the maximum of these probabilities by small p. Okay. Then, suppose you give me an arbitrary tensor T. Let me just do it for where n1 to nr are all equal to n. So r to the n's tensor product with itself arc times. Okay. So T is T could be a deterministic tensor or a tensor independent of this, right? What I am doing is essentially I'm keeping some of the entries of T alive by doing a Bernoulli sampling, right? So that's basically boils down to multiplying the corresponding element of T by this. Okay, maybe I'll call it A, the Bernoulli one. So I'm looking at this element-wise product tensor, whose I1 to IRth element is the product of the corresponding tensor elements. Okay, so basically, you for each of the entries, you are doing a coin toss with probability P1 PR, right, and keeping it if you get a success, right. So basically, a sparsification of the original tensor. Okay. So here is the result. Again, this is something I won't prove, but using this, you will prove certain versions using unfolding. So, but this result is quite useful. So if you compare this sparsified tensor with its expectation in the operator norm, okay. So let me write it in this way. So this is O of square root NP. P is that maximum of all the Bernoullis, Bernoulli parameters up to a log factor. So this log factor is possibly suboptimal, but polylog factor. And you also need the maximum of the EIJs. Okay, with high probability. So I'm allowing a sparsification, and that is being captured here in this MP. So if you have seen so for the corresponding matrix version, the largest the operator norm of a Wigner matrix, or that scales like square root, and that we have discussed earlier. But if you take a sparse random graph, right, there the largest eigenvalue scales like square root of the degree, which is n times p. Right? So this is in a similar sense. So let me write. So this is only valid in a certain regime of p. So valid for p bigger than c log n over n. Yep. So the proof is essentially, so you have to again analyze the multilinear functional over the product of the spheres, right? So there we did it very crudely, right? We got a sub-Gaussian for any arbitrary x1 to xr. To capture the effect of the sparsity parameter, you have to be much more careful. You have to basically split up. So there we had to look at this type of objects. Okay, one I1 R IR, the sum over I1 to IR. So this was one of the entries, right? In that, so this is what we are optimizing over. So in order to prove this, you have to also see on what kind of sets of indices give you, large contribution from this product, right? So you have to break this into two parts. The part where this product is large, that you have to analyze very carefully. The part when this is small, that is something that you can take care of using that technique. So this is unfortunately a bit too complicated for to do here, but this is a very famous argument of Khan and Zemeredi. So if you are interested, at least the matrix version of this you can find in a paper of Ley and Rinaldo from 2015. Yeah, matrix version also needs p bigger than log n. So that actually can be explained if we for at least for the graph case. So if you have a sparse graph, like bounded degree graph, right? So that is like NP is like a constant. So in that case, you can show that there would be high degree vertices. So there would be at least one vertex whose degree is like log n over log n. Right? Now, if you have a high degree vertex, that creates a star in the adjacency matrix. The eigenvalues of the stars are large, right? Because the degree is large. So that will create a large eigenvalue. So this bound is saying that the operator norm would be of constant order, so that will fail because of the presence of a star. But then what people do is you can prune the large degree vertices, then you can still again recover a concentration result like this if you prune the large degree vertices. Okay. If you are interested, I can. So this is not difficult to do. I will add a guided exercise where to show this essentially. Okay, so that is the reason why I need at least NP going to infinity. But for tensors, it's not clear. So this is clearly the range of validity is suboptimal. Why? So for the graph, NP has a meaning. It's the degree, right? So NP being constant or going to infinity has a meaning. So this is the suboptimality of this method. But fortunately, you can bypass it by using that cheap trick we were referring to earlier. So take a tensor, unfold into a matrix. That's a sparse matrix. You can apply the matrix version of that result, and that would give a upper bound on this operator norm. it turns out you get the right upper bound, because you see the right upper bound is again of the order of n square root np by that result that we proved, the lower bound that we proved. So for other ranges, sparser ranges, of P, can use unfolding to control it. Yeah, so this you can, this is a simple exercise actually. So I'll define what I mean by unfolding, and then this can be a simple exercise. Okay, so let me, yeah. So in that setting, so let T be a tensor, R or so what we'll do is, so remember, so yeah, I think I explained it last time. If you have a order 3 tensor, unfolding basically groups the indices into, boxes, and each boxes will linearize into an, in column measure or in some measure format. So that gives you a smaller order tensor. That's what unfolding is. So let me precisely define it. Okay. So pi is a partition of 1 to R. And so all the particular way of indexing into the smaller tensor. Okay, so this should be n to the R, and this should be mapped to n to the, so these are the blocks of the partition. Okay, so pi is a partition of R. I write pi as a, union of, so these are the blocks of this partition, B1 pi of BL pi. Okay, and this gives me the indexing. So let me call it phi of pi. So phi of I1 to IR. So that would be mapped to, so that is M1 to ML. So I'm starting with an R order tensor. I'm grouping the indices and ending up with an L order tensor, right? And I mean, this is one way of. Okay, I realize that this is not worth writing. Something like this. So, some column measure or some measure format. So point is, you unfold the tensor into a smaller order tensor. In the smaller order tensor, we can use this result, and that will give an upper bound on the original operator norm, because this inequality, the operator norm of a tensor is always less than or equal to the operator norm of the unfolding. So I would add some exercises again for you to derive the optimal results in the other regimes of sparsity, where P could decay like log n to the alpha, right? Okay. All right. Any questions to this? Yes. Yes.
Who is the tensor?
Yes.
Form r to the power of n1, tensor r to the power of n1,
Okay.
tensor r to the power of n2, tensor r to the power of n2. You can think of that as the tensor product from matrix.
Yes.
And you can think of it as big matrix.
You can think of this as a big matrix. Yes.
Parallel theory, if you think about it, that line
A tensor product of matrices.
just want to do all these.
Yeah, I guess some of these arguments you can definitely do there, right? Yeah.
But then the other tools that you can use.
Maybe I'm not sure. Yeah, but these tools are pretty robust, so should be able to buy them.
So, but there you can talk about honest singular value.
Yeah. Once you have matrices, you can talk about on it. In fact, yeah. So you can talk about vectors of singular values, etc.
But art, every art.
L tuple, yeah. M is the, where do you send the? So let me just explain it like this. So here you have like these. So let's say I partition into 2 blocks, right? So what I'm doing is I'm re-indexing these numbers. This into in a linear array. These are the, I think this is the column measure one. So any other questions? Okay. So now I want to move to another topic. We have some basic tools now to control the operator norm of a tensor, right? So now I want to talk about contractions of tensors. Okay. So we have already seen them. So this is one contraction of this tensor T. And you get at the end a scalar, right? I sum across all the modes. But if you sum across all but one modes, you get a vector, right? So I can decrease this, and you can get even tensors, matrices, etc. out of it. What can you say about them? Okay, that's the next topic. So in particular, I will focus on matrix valued contractions. In this case, if T is a R ordered tensor, I'll just contract it along R minus 2 the directions x1, 2. This will produce a matrix because I have kept 2 indices free, right? I've summed over all the R minus 2 indices. So what can we say about the spectral properties of this matrix? That's kind of the next question. So first order of business is, you see that, so what kind of model would we assume on T? We'll assume that the entries of T's are typically independent random variables, right? And you are then contracting, so you're summing up a lot of those coordinates. So at the end, you get dependent random variables. So you get a matrix whose entries are highly correlated, right? So this gives rise to In fact, I think this is also true. So we looked at this form, right, when we talked about, we were talking about the eigenvalues. And to show that there is an eigenvalue, we optimize this form over the unit sphere, right? So the gradient of this form looks like this vector, right? What about the Hessian? This will precisely be a contraction, and you get a matrix, right? And it's proportional to I think there is a constant of R, but C times C prime times. So in some sense, we are looking at the that Hamiltonian, and we are looking at the Hessian of that Hamiltonian, right? And studying the eigenvalues of that will tell you whether you are at a saddle point or at a local minima or a global minima, etc. So studying these matrices is important. I will give you one more natural example where this type of contraction show up, and that is in the context of hypergraphs. Recall, so you have an adjacency tensor. Is an hyperedge, right? So there is one matrix that is quite popularly used in hypergraph theory. It's called the adjacency matrix. Okay, so let's denote the tensor by script A. The ijth entry of this matrix is given by the number of hyperedges containing both I and j. Okay. So this is a n by n matrix. And can you see how is it related to the adjacency tensor? Sorry. So hyperedges are just subsets of indices, right? So like if me, you, and some other person here are friends, we form a 3 hyperedge. Right? So edges are pairs of vertices. Hyperedges are subsets of vertices. Right? So I'm taking an R uniform hypergraph. This is the adjacency tensor of that. I can also associate an adjacency matrix where at the ijth entry, I basically count how many hyperedges are there containing both I and j, right? So this matrix is in fact a contraction of that of that adjacency tensor, right? So this is the all ones vector. You're summing or contracting along that. I think you have to divide by some normalizing constant depending on R, but other than that, this should be the relation. Okay.
And so without the normalizing constant, basically each entry should be anything from 0 n minus.
Each entry could be 0 to n minus 2 choose R minus 2 because
So then would that be by the normalizing constant?
there is some permutations issues going on, so I guess you should figure it out. Yeah. But other than that, this is what you get, right? So our plan is to now study the, so random matrix theory is quite well developed. but these are correlated random matrices. So what can we prove about these correlated random matrices? Okay. And immediate application would be to this setting, the adjacency matrix of a hypergraph. Uh, so, well, I'll cover the hypergraph case first, and then move on to a generic contraction. Yeah, so the normalizing constant is actually r minus 2 factorial if you work it out. But anyway. But it's a symmetric random matrix. It's a hypergraph, right? Yeah, you are right. If things are, all the entries are uncorrelated, you'll still get a uncorrelated random matrix. Okay. Let's see. So here is one model. So I will assume that the entries of this adjacency matrix, I1 to IR, they're independent. In fact, IID Bernoulli P. So this is a generalization of the Erdős-Srény random graph. All hyper edges are of size R are present with probability P. Okay. Very soon. I will of course assume that loops are not present. They will not matter for spectral questions that will ask. The loops here are, a subset of vertices where an index is repeated, right? So let's say II is a loop in case of a graph. In case of a hypergraph, this constitutes a loop, right? So these are not there, right? Only R subsets are present. So that's the assumption.
Any ordering
So typically when I say hypergraph, we are talking about sets. So these are undirected, right? Completely undirected. So this gives you a symmetric tensor basically. Right? Because things are undirected. Okay, so my claim is that in this case I can take this adjacency matrix where the ijth entry counts the number of hyper edges containing both I and j. So that can be written as a linear combination of okay, so let's see. Certain matrices. Okay. So these are, what are these? These are hyper edge indicators. These are precisely these Bernoulli variables. So I'll just write it in this notation. If E is present as a hyper edge, so this is Bernoulli P. Okay. So these are IID Bernoulli P, and E's are enumerated. E belongs to, I mean, by an abuse of notation, I will say that E vary between 1 to n choose R. Okay. So as I was saying, we are summing up the entries of the tensor, so that creates correlation, and you can actually write down this expression for A. So A is a linear combination of certain deterministic matrices, and the coefficients are precisely these hyper edge indicators. Okay. So what are these QEs? So QE is this matrix. So this is not difficult to check. Where A is the indicator of that hyperedge. So AE is a vector whose ith entry is 1 if I belongs to the hyperedge and 0 otherwise. So vertices which are present in the hyperedge, you just place a 1 in that vector, otherwise you put a 0. So it's just like an indicator vector of the hyperedge. So then you can represent this A in this form. And so now what we'll do is we'll suitably normalize things. So you look at the matrix A tilde, which is A minus expectation of A, and divided by the entry, the standard deviation of this Bernoulli's. So see, then I can rewrite this as again as a combination of this deterministic matrices, right? But these are now mean zero variance one random variables. IID means zero random variance one random variables. So Y is IID mean zero variance one random variables, right? So therefore, so what we're going to do is associated to so coming from this hypergraph, we have ended up with matrices of this form, but now I can generalize. So these are Bernoulli's. I will just place arbitrary zero mean unit variance random variables here, and that would give me a new ensemble of random matrices which exhibit correlations. Okay. So given y1 to y n choose R independent zero mean unit variance random variables. I have now defined an ensemble of random matrices in choose R given by this. If R equal to 2, you get back the adjacency matrix of a random graph, right? Of an additional random graph. So what I want to do is I want to study the eigenvalues of that ensemble. And so in particular, the spectral distribution, the bulk spectral distribution, the largest eigenvalues, etc., etc. So what happens in the R equal to 2 case? R equal to 2 case, you just have an Erdős-Renyi random graph, right? So in that case, it's known that the limit distribution is a semicircular random variable. So you get a adjacency matrix of an Erdős-Renyi random graph. Okay. So then if you look at the empirical spectral distribution of the corresponding matrix, okay, so this converge in an appropriate sense to a semicircle random variable. Let's almost surely. Okay. So so this has a density four minus x square dx. Okay. In the case of random matrices, this is true as long as NP goes to infinity. The degree of the graph, average degree, goes to infinity. Okay. What happens to the largest eigenvalue? The largest eigenvalue, as you can guess, converges to the endpoint of the support of this law, which is 2. Okay. So I think for this, the best known regime is you need degree to be at most log to the 4n. That's kind of the best known regime where this convergence is invalid. Okay. So this is what you know for random graph. I want to ask the same question for that ensemble of random matrices.
Degree going to be something like order.
The max degree, this is also going to be of order root n, yes. 2 times root n. If you don't, I see. If you don't, so I've already centered things, right? So if you don't center it, you have a rank 1 matrix. So that's like order n. This is the largest eigenvalue of the centered matrix. I've already centered things. Yeah. So turns out something interesting happens for that ensemble at the edge of the spectrum. So that is for the largest eigenvalue. There is a phase transition. Okay. So you still get a semicircle law for the empirical spectral distribution, right? So that converges to a semicircle law again. But something interesting happens at the edge. So you need a different normalization. So let's. So this is the largest eigenvalue of the, yeah. Not really, I am already working above the connectivity threshold, so yeah. For the sparser regime, the limit that you get is very complicated when NP is like a constant. So that is also has been very recently obtained for that ensemble of random matrices. That's related to, so for the Edo-Shreni case, locally it looks like a tree if things are sparse. So basically what happens is that the limit of that spectral measure converges to the limit of the corresponding Galton-Watson tree. So you can associate a spectral measure to the Galton-Watson tree associated to that corresponding branching process. There is a similar description here as well, okay, for that ensemble of matrices in the sparse regime. But for the eigenvalues, I don't know of any result, the largest eigenvalues, which are applicable to the sparse regime. Okay, so let me write down what happens here for that ensemble of random matrices. So I'll read another normalization. So I think it is, yeah. So lambda max of A tilde over n minus 2 choose r minus 2. This is coming from the fact that I'm counting the number of hyperedges that contain both I and j, right? Divided by square root 2, and in addition to that you have the square root n, right? This is the correct normalization. So you can show that this converges notionally to 1 over square root r minus 2 plus square root r minus 2. Okay, so r is fixed. So for the graph case where R is 3, I know that it converges to the endpoint of the semicircle law, which is 2, right endpoint of the semicircle law. As I told you, the bulk spectral distribution doesn't change, right? It's still the semicircle law. So when R equal to 3, you still get 2. So the largest eigenvalue again converges to the endpoint of the semicircle law. R equal to 4 onwards, you are detached from the largest eigenvalue, from the endpoint of the from the support of the bulk. So there is a phase transition happening at R equal to 3. Yeah, so I'm leaving 2 coordinates summing over all the rest of the entries, and this is the interpretation of the ijth entry. Exactly. The correlation gives you this. So if you look at this particular structure carefully, this is what you see for spiked random matrices. So there is something called the Baig-Benner phase transition. That is what is giving you this phase transition here. I'll tell you what that is. But yes, time is almost up. So maybe I'll pick it up from here next time. So let me just write one line. So the moral is there is a phase transition at the spectral edge. At R equal to 3. Okay. And really interesting things happen at R equal to 3 if you try to find out the fluctuations around this limiting value. Okay. And that is still open. I'll tell about it in the next lecture. Okay.
Because of that, I think that we took my, Shimon activities question, before we talk about.
Awkward silence before we open up to Mr. On the console.
So there are any students with questions or comment to counter the answer? Please go ahead.
What the hell is going on? We're not allowed to ask them. One good, one last. You go to the test.
Yeah.
So it's like upper bound and lower bound for the spectral norm. That would also generalize to the case where like, N1, like the NI, they're basically different. Like you still have like that, like the square root log R summation NK and
Yeah.
upper bound, and you have like summation NK square root is like a lower bound.
Yeah, so this construction already tells you that the max of square root n1 and 2,
Right.
that's just like a Vermont.
Yeah, so basically what I was wondering is like, and of course now when the NIs are different, you can't talk about like a tensor being symmetric one.
If n are different, then
Different than saying then it would make sense to use the word.
no, of course not.
Yeah, so basically I'm wondering like what results do we have that's more general to
I mean, so far we just talked about the how the spectral norm behaves, right? I think much of this for the Gaussian case, the behavior of the at least the number of critical values that you can still study using these techniques.
For example, maybe like a tensor product of like instead of like R and N1, what if you had like matrices N1 cross N1 matrices and tensor matrix N2 cross N2?
I see. Yeah. I mean, the non-asymptotic techniques are pretty robust, so those will work. But I'm not sure whether these. I mean, the Katz-Rice formula is still valid, but whether you will be able to handle it, whether that's.
Like this, R uniform hypergraph, right? But what if we like try to do it like as like a true like generalization like hypergraph of like let's say like the Evergreen graph, so that you allow all hypergraph, but then maybe you can make it like a tensor product of like R uniform.
That can be done with this technology. I mean, you have bunch of tensors, each of a different order. You can simultaneously study the area. That can be done using this representation. Yeah, it can be done. So in fact, so if you allow, so in this setting, if you allow different order hyperedges, and let's say on an average, there are each vertex belongs to one hyperedge of order R, then you can show that the limit would be semicircle with variance pi square over 6. So somehow zeta 2 pops up.
But wait, this is, we have the result. From there, then we go to 4 tensors, order 4, then order 8 and so on, and then somehow interpolate in between. So that order 4 I got 2 matrices kind of thing, you know.
Oh, I see what you're saying. Yeah, I mean, you can of course get inequalities and but yeah, like interpolation inequalities, but not sure whether you get sharp results.
From a computational perspective, suppose I want to find some best sort of track approximation of the tensor.
Yeah.
Some
Yeah, so if you're a theoretical computer scientist, there is a JCM paper. Title is Most Tensor Problems Are NP-hard, and all of these are NP-hard. Practically, you can use power method. Power methods would converge to the top eigenvalue given some accuracy. Like if you want an epsilon approximation to the largest singular value singular vector, you can apply power method.
I put some like alternate squares when I fix for all the one factor, I fix all the other factors.
You optimize over. Sure, you can do that. I don't know whether it will converge. Yeah. Yeah. So in fact, this question reminds me of something. So we talked about eigenvalues. So there is a more computational notion of an eigenvalue. So eigenvalue is called robust if the power method always converges to that eigenvalue. Like you have exponentially many eigenvalues, but there are certain eigenvalues which are robust in the sense that in your power method iteration, you start with some initialization, right? So these eigenvalues have some domain of attraction. So if you initialize from certain part of the space, they will converge to that eigenvalue. Those eigenvalues are called robust eigenvalues, and you can prove that there are always at least n robust eigenvalues. But I think power methods is what people use, but what you suggested that can definitely be used, but I don't know whether
That's the one, that's some overparameterization. I mean, that is the you some higher rank approximation. I mean, then it may be more of a stable.
I see. Yeah. No, I don't know. I mean, yeah. So
So I can comment on that. So there is a problem called the spike recovery problem. The standard spike recovery problem. There, so given the samples from the standard product of K is Gaussian, the spike covariance like structure. And then the goal is to get recovered the top tensor of the artist for top of So what people do is like the value of the spike problem.
yeah,
Spike problem. And given for K more than 2 studies.
it's NP-hard, right? You can.
But they do like a spike criterion, right?
Yeah.
That maybe different theoretically something exists for the samples. But like if you give an n square sample,
Then you could do it. Right. Yeah.
Mentioned that Belarus work on this. What is the motivation for that?
Their motivation is to study the p-spin spherical spin glass. Like study the surface of the Hamiltonian. Yeah.
And
That basically is like the rank 1 tensor model. So there is a follow-up work where they take the, this is like a null model where you have only noise, but you add a rank 1 spike, and then you can study the loss surface of that whatever objective function is there. Yeah. Yes.
So, this maximal eigenvalue that you mentioned, it's asymptotics, in the specific setting of R.
Right.
It's one process.
like the eigenvalues which are close to the maximum.
Right. So all of them will converge to 2, right? So there is eigenvalue rigidity result. So if let's say you order the eigenvalues, like 1 being the largest, then if I over n converges to alpha, then the eigenvalue will be close to the alpha-th quantile of the semicircle now. So there is a strong rigidity result. So those are like the population counterparts of this sample eigenvalue, and there are very sharp approximation parameters.
1 by square root after symmetry.
No, it's not yet there.
And that so would answer the question saying like the spacing between eigenvalues.
Yeah. So the bulk spacing we do know, but the edge. Yeah. For r equal to 3, there's a conjectural spacing behavior coming from the Gaussian case, but we don't know whether it is universal or not, whether it applies to the Bernoulli case.
So the associated point process, we still expect the same sort of repulsive picture.
I think the same. So the largest eigenvalue still is given by the Airy process and the time process. Yeah.
Again, sort of motivated by random matrix theory, like a pretty powerful tool for a wide variety of matrices is the use of interlacing. Like you have interlacing identities. So there's something. Is there an analog in
For 10
symmetric tensors?
The trouble is we haven't even looked at the bulk distributions yet, right? We have just only looked at the critical points of that form, and they only give you z eigenvalues. So we're not even covering all the eigenvalues. Yeah. So the problem is for random matrix, the one consequence of this beautiful trace identities is that you can apply moment type calculation or still just transform based calculations, etc. So there is no moment, trace identity relating the eigenvalues to powers of the tensor in some sense. So that avenue completely breaks down.
In a sense, also there's no like expansion in terms of minors.
Yeah, exactly. Yeah. So I'll talk about it in maybe the last class. So there are certain analogs of still-less transforms for tensors. They are not connected to eigenvalues, but you can. At least people haven't figured out if there is a notion of eigenvalues which correspond to this. But
Like a measure for like singular values.
You can get a measure, but it's not that's the question. Is there a suitable concept of a singular value such that this is the Still-less transform of that measure? So it's not known.
Wide open.
Yeah.
That eigenvalue which I forgive.
Sorry. Z eigenvalue. Yeah.
You will be able to compress videos output like STD for the images for STD and compress, right?
Those are that's more like low rank representation, like best R rank approximation. Unfortunately, those are not directly related to the Z eigenvalues. Yeah. So there is a class of tensors called orthogonally decomposable tensors, which have this type of orthogonal, you can write it as a sum of orthogonal rank 1 tensors, right? This is a subclass of tensors. Just to motivate, like, where do you see this type of arrays of numbers? That's it. But some of the things that we have, so the spectral norm bounds are still useful, right? For approximating a tensor by some, some deterministic tensor, for instance. So think of of a block model, right? So the expected adjacency tensor captures information about the blocks, the community structure, right? So if you, in some sense, can show that the adjacency tensor is close to this expected or deterministic tensor, then by analyzing the deterministic one, you could hope to recover the guarantees on the community recovery. Random cluster model, how I don't. But the form is not like that, right? So yeah, I don't know. So there you have the, an Edoshrani type thing, and then a cluster. Yeah. I mean, you can generalize, I guess. Some Edoshrani part would for the hypergraph, and then not like a tensor. Yeah. Sorry. What do you mean by conjugation type things? Change of basis, no. The operator, that norm is the Frobenius norm that we define, that is invariant as a change of basis, not the eigenvalue.
Yeah, what about the singular values then? Question.
Singular values, yeah. Singular value would be by definition, right? So the operator norm is also unitarily invariant.
I think potentially like in interest of us actually getting to ICSR on time that maybe conclude the day's events. Okay.
Okay,
So you might
thank you.
that's thank our people and
managed to walk to ICSR. Walk cafe because people